Oh, I'm so sorry.
Boy, that sure silenced everyone, huh?
It did. It sure did. Book Davies was the first one to log in. He goes woot. Chris Larson says woot woot.
Hey, Scott.
I love the audience. Yes.
Scott, when we talk meteorites, I'm going to be showing them
Cool.
and trying to get them to appear okay and in relative focus near the camera. I don't know if you kind of want to have maybe a little conversation with me as I do this, because I'm going to be pulling things out and showing them to the camera.
Sure.
And it might help as a little conversation with you a little bit, if you want to chime in a bit.
Sure.
Okay.
No problem. Like maybe challenge you, like, is that really a meteorite?
Dave, I know that you're totally full of crap on Camel Donga there. Okay. So don't try
you
to
found
get
those in the backyard, right?
Be as assertive as you like. We don't have enough hecklers on
we have
Scott,
no.
Yeah.
Oh,
it kind of spices things up a bit.
I like to heckle Scott. I heckle Scott.
Yeah, he does. Yeah, he does it live in person, right in my face, so.
I'm not afraid of Scott too much anymore.
Yeah. Right. Oh my goodness. Well, I saw at the on the news, the airports are starting to have COVID testing right at the airport. It's kind of a new thing, so
that's interesting.
you can either pay $75 for a PCR test, or you can pay $200 for a rapid test. And so the airlines are requiring that you have a test, some of them like within 4 hours, okay, of you getting on the plane.
That's like paying for extra baggage.
Yeah.
Yeah.
Yeah, I know someone who went. I think he flew down to Aruba. He and his family all got tested before they got on the plane, but when they got to Aruba required them to get tested again before they were allowed to leave the airport. I think that was like a tourist fee or something. I don't know.
Well, I went to Central America around December. And of course, I had to have a test to get in to Central America, and there was doctors waiting, and there was a long line, and we all had to get our paperwork checked and everything. Coming back at that time, there was no test at all required to come back to the United States. So you could just hop on the plane, no one was tested. So they've changed that now, which is a good thing. But they say that aircraft are some of the safest environments that you can be on, because the filtration system on an aircraft is, just scrubs the air so many times. So, but
well, at the rate of inoculations, at least things will be much safer 3 months from now.
That's true.
As far as air travel goes.
Yeah. David, you got your vaccination, right? Mr. Levy?
Yeah, I got my first one. Wendy and I got our first ones, and our second ones are scheduled for March the 31st. And that evening, we're going to go out and party.
That's right.
We're going to join all the co-eds at the in Miami Beach.
Yeah. Spring break.
Just kidding, everybody. We're going to continue doing what we're doing.
I can just imagine this giant jumping crowd and stuff, people, and it kind of zooms in on Wendy and David. Yeah. Mr. Levy and I have had many a very funny and strange conversation. So it's fun.
Yeah.
It's fun to hang out.
Really do enjoy it.
with.
Actually, Jerry and I had a good one yesterday.
Oh yeah, we had a great workout. Yeah.
We had our own private Zoom session.
Mhm.
Jerry did a wonderful job getting my telescope connected to a newer computer, and just working on the camera now. So the telescope's connected.
Well, David, I just saw a movie. I was curious if anyone else has seen it. It has to do with comets acting like asteroids, I guess. It's called Greenland.
Oh yeah, I saw that. My wife and I watched that the other night.
Yeah, a big. It was a comet, extra solar comet, and it ended up hitting the Earth, and it had multiple pieces. So it was an interesting premise. I thought it was fairly well done, except that for the big chunk to be an extinction level event, I thought they had the pieces coming in at much too shallow an angle. It would have to really come much more vertically and punch through the atmosphere and do that type of damage.
Yeah, my whole skepticism with the movie was how quickly the nuclear winter ended. I think they were only underground in Greenland for like 6 months or something like that, or 9 months.
9 months or so. Yeah.
I think that would have been years that the Earth would have been in a nuclear winter or a winter.
Yeah, I don't know. Our main skepticism was the thought that the government could be competent enough to organize such a big thing so quickly.
Yeah, that's probably the biggest fallacy in that movie.
Yeah, if they were an asteroid or comet large enough to be a potential civilization killer and cause a nuclear winter scenario, that would go on for years.
That's what I thought.
That extinction in the atmosphere. Yeah, I haven't seen it, but I'll have to look out for that. Yeah, but you mentioned.
Okay.
I'm sorry.
Go ahead, David.
You mentioned asteroids and comets. There used to be a very clean line of distinction between the two, and not anymore. Now they're comets that act like asteroids dynamically, and vice versa. So it's interesting now.
Yeah, it was definitely worth watching, and the global. The view of the globe after it was all said and done was kind of interesting. With all the craters.
It is Hollywood, so.
Yeah. It was, yeah.
The old throwback to the KT or KPG impact, a 10-kilometer rock can ruin your weekend.
Yeah.
Yeah, I forget how many miles or this thing was supposed to be, the big chunk, but
there aren't any civilization killers, of course, in near-Earth orbit among the many NEOs that are that large. But of course, as you mentioned an interstellar comet, there could be things that come from in back of the sun or from another solar system that are not in the NEO database, or unknown, that could be a problem.
Seemed like, kind of early on, every time that we saw an NEO, it was like, wow, that was close. Wow, that was close. We saw them afterwards.
Yeah.
It's probably that way with a lot of PHOs now.
Well, and we still only know of about, 3 or 4%, I think it is, of the rocks that are relatively close that could be sort of regional catastrophes.
mm-hmm.
So that's, there could, if you look at the major impacts over time in early Earth history, these aren't going to stop because we're aware of them now.
No.
So this will happen at some point again.
Yeah, it's like you hear that knock in your engine, and you try to ignore it for a while, and you go, I'll bet that's the whatever.
Yeah.
Turns out that's always what it is.
Yeah.
Now, I just read about, I think it was in the astronomy magazine, about the one that the the asteroid that was discovered not too long ago that came close a week or two ago, and every 8 years, and I think in
Is it Apophis?
Probably it's this one.
yeah, in the 2030s it'll get close enough to be Mag 3 or so, but I guess in 64 is when it could be problematic. Something out
although
there.
I think it's unlikely to actually be a collision scenario, but everyone likes to blow the horn and make a story out of it. But a lot of of course, this stuff comes raining in, every day, small pieces. So many tons a day, and a lot of it is just cosmic dust that's very small. But there will be some impacts in the future. Unless
the thing that was interesting in that article that I hadn't thought of before was, well, I guess without Arecibo, they were trying to nail down the spin rate, because spinning, I didn't realize how much spinning would have an effect on its motion.
Mm-hmm. Yep, and now really there's no literal replacement at the moment for Arecibo either. There's the FAST telescope in China, but that's not a one-for-one replacement, especially in terms of radar, so we need to build another giant radio telescope at some point, it seems here.
Yeah. And they said it would take, what, $50 million to build another one or something?
Yeah.
They have a study going right now how to replace it with a much better instrument I think it's going to be like 10 times more sensitive, maybe. I don't.
Worth it. I mean, think of what we learned from Arecibo. My God, it was
tremendous amount, and it was ancient technology. It was first, built to study the ionosphere. Listening for nuclear explosions at the end of the 50s. It was a crude instrument compared to what you could do now.
Mm-hmm.
Well, the Tesla or Amazon guys have that's pocket change. They could replace it, without thinking about it.
Exactly. Yep.
I think they're more like, let's just build a colony on the moon instead. I don't know. Of course, they should have something to communicate with the moon.
Welcome back.
Right?
Maybe they'll decide to build a big, huge radio telescope on the dark side of the moon, on the back side of the moon, I should say, and in a big crater that's like 5 miles in diameter or something.
That'd be cool. So did any of you sign up to go on the trip around the moon? There's a guy in Japan that is doing that. I signed up. We'll see. Good Lord, we've already received 100 messages.
That's good.
Yeah. John Johnson's on. He's from the Nebraska Star Party. Andrew Corkill, dedicated amateur astronomer with now an observatory. It's very cool. Cameron Gillis out of Seattle is watching. Martin Eastburn. Here we are again with the rain in the East Texas, cataloging books as I watch and listen. We have a global star party happening on the 23rd, and that is the anniversary of Draper. Was it Henry William Draper? Is that right? Made the first photograph of the moon in 1840. So I'm thinking of having a moon-themed global star party.
Oh, cool.
Indeed it is. It is also the anniversary on the civil date of the discovery of comet Shoemaker-Levy 9.
Wow. So we should...
We definitely have a Shoemaker-Levy Day.
Yeah. Maybe I know someone that can host that.
Evidence that a planet of a distant star lost its atmosphere, then gained a second one through volcanic activity, according to scientists using NASA's Hubble Space Telescope. The planet, GJ1132b, is hypothesized to have begun as a gaseous world with a rocky core. Starting out at several times the diameter of Earth, this so-called sub-Neptune quickly lost its early hydrogen and helium atmosphere due to the intense radiation of the young hot star it orbits. Then, the planet was stripped down to a bare core about the size of Earth, and that's when things got interesting. To the surprise of astronomers, Hubble observed an atmosphere which, according to their theory, is a secondary atmosphere that is present now. Based on a combination of direct observational evidence and inference through computer modeling, the team reports that the atmosphere consists of molecular hydrogen, hydrogen cyanide, and methane, and also contains an aerosol haze. Scientists think hydrogen from the original atmosphere was absorbed into the planet's molten magma mantle, then slowly released through volcanic processes to form a new atmosphere. Though this hydrogen continues to escape into space, the secondary atmosphere is replenished by volcanic gases that seep through cracks in the planet's thin crust.
Cool.
Scientists are wondering how many other planets might have started out as gas giants but became smaller and rocky after their early atmospheres evaporated away. Astronomers hope to use the upcoming James Webb Space Telescope's infrared vision to detect hot areas of volcanic activity on the planet. GJ1132b might be orbiting a distant star 41 light years away, but thanks to the Hubble Space Telescope, it just got a little bit closer.
Awesome. Well, that was cool. Yeah, I love those little videos from NASA and the European Space Agency that we can broadcast. It's a great outreach tool. If any of you are astronomy club presidents and you do video programs like these broadcasts, get in touch with me if you don't know where these things are, but they are freely available for download and they're royalty free. So it's excellent. We have a fantastic group of people on tonight, including the Rappahannock Astronomy Club president. We have Myron Wasuda. He is the president of the Mark Slade Remote Observatory MSRO Science Organization. Dave Dowell, he's up there in the cold, super cold Canadian North. David Levy here with his beautiful telescope. David Eicher with his beautiful telescope. David Eicher's editor of Astronomy Magazine. David Levy, of course, discoverer of Comet Shoemaker-Levy 9, which we were just talking about. Its anniversary of discovery is coming up very soon. They are keynote speakers here. Richard Grace, the Astro Beard, is with us. Lauren Lennon, still in warp drive, okay, from the Mark Slade Remote Observatory. I understand you're a trained professional astronomer, is that right? That must be right.
I'm sorry, I was on mute. The life of a Zoom meeting, right? You better be on mute.
Yeah.
But yes, I have degrees in physics and astronomy from Case Western Reserve.
Awesome.
And I'm on the board for MSRO as the staff astronomer.
Fantastic. Max Dubnowski is with us tonight. Our co-host, Jerry Hubbell. Jerry is Vice President of Engineering for Explore Scientific. He is, I don't know exactly what title or role that you have with the MSRO, but I know that you're one of the founding members. And
I'm the Assistant Director of the Observatory and the Vice President.
Yeah, and that's awesome.
Mm-hmm.
Alexandros Philothodros, did I pronounce Philothodros? Sorry.
Yeah.
Okay.
Yeah.
I got it. Okay. Yeah, he's from Greece. He's got an excellent connection. You guys have fast internet over there. That's awesome. Carol Orge, president of the Astronomical League, is with us right now, and not the least, Livy in the Stars is with us too, in front of a beautiful Milky Way galaxy. Being that this is co-hosted by the MSRO and Jerry Hubbell has so graciously agreed to be the host to invite or to introduce all the speakers, I'm going to turn it over to him. But I do want to say that Jerry has devoted much of his life to educational outreach in astronomy. And what he's doing today with the Mark Slade Remote Observatory, the books that he's written, the lectures that he gives, all of these things, he has really done an incredible service for the astronomy community, both amateur and professional. So I'll turn it over to you, Jerry.
Thanks, Scott. That's that sounds a little overblown to me, but that's great. No, that's awesome. I appreciate that
true.
introduction. Yeah, it is. It's
all true.
But so thanks, Scott. So I want to. Our keynote speaker is always at the Global Star Party. It's my pleasure to introduce world famous astronomer and comet discoverer, Dr. David Levy. I've really become friends with him, and I really appreciate that I had the opportunity to meet him back in 2014 in Tucson during the imaging conference in December, I think, of 2014. And we had a great conversation at dinner. So I'll always remember that.
Well, thank you so much, Jerry. And we actually had a good conversation only yesterday.
Yes.
And I really did enjoy that day. It worked out very well. I think what I need to do is to start throwing telescopes across the field to get the cameras to connect. But
right.
Wendy says that's not the way to do it. So I listen to Wendy all the time. Anyway, I want to welcome you all to this Global Star Party, our 37th. And I kind of enjoy this, Scotty and Jerry. I think I'd like to join a few more, if you don't mind.
Okay, all right.
Yeah. Anyway, I always begin with a quotation of some sort. And today, all of you literature buffs know that there was only really one choice for a quotation, one day after the 15th of March. And the quotation must come from Shakespeare's Julius Caesar. And in Act 1, Scene 2, Caesar is sort of in his motorcade, sort of going down the street, when the soothsayer comes out and says, "Beware the Ides of March." And that was yesterday, as you all know. And then 2 acts and 1 scene later, Julius Caesar is on another motorcade and he sees the soothsayer again and he says, "The Ides of March are come." And the soothsayer looks back and says, "Aye, Caesar, but not gone." And then we all know what happens in the Senate House a few hours after that. So this is my quotation for today, but I'm also going to add an astronomical one. This one from Leslie C. Peltier, Starlight Nights. And when I first heard about Starlight Nights, I was a teenager, and I heard about it from Isabel Williamson. And she quoted something that I've never forgotten, and I'm going to quote that now. He writes about comets, and here's what he says about them. "I had watched a dozen comets, hitherto unknown, slowly creep across the sky, as each one signed its sweeping flourish in the guest book of the sun." And now, Jerry, thank you. Back to you.
Awesome, David. That's great. Yeah, beware the Ides of March. I remember that. I took 4 years of Latin in high school, so I'm kind of a geek that way, I guess. I don't know how many people took Latin in high school. But no, that's great. So our next keynote speaker is David Eicher, the chief editor of Astronomy Magazine, which everybody here is very familiar with, I'm sure. I love Astronomy Magazine and enjoy it. I've been given the opportunity to write an article last year. That was awesome. And I want to thank David for that. And I've met David a couple times over the years at the NEAF shows in New York, and actually got a picture with him to prove it. So, so So I look forward to hearing about, you're going to talk about meteorites, isn't that right, David?
Yes, that's right, Jerry. Thank you so much for the introduction. And thank you, David. It's always such a pleasure to have David kick off these events with his thoughts, which are very inspirational. And thanks for having me, Jerry, and Scott as well. I've been talking about a lot of astrophysics these days, but I thought I would step out of that just for a week or two and talk about some objects here, because they're piling up here, reorganizing things. My father infected me with a lot of interests, science and history and other things. And one of them was mineralogy, which he was very interested in when he was young, taking trips out to the west from Ohio in the old days. The first one that he took with his family, believe it or not, was in 1926. And in the 1920s, 30s, and 40s, you could collect a lot of samples yourself, which you can't really do in the era of attorneys and people possibly falling down mine shafts. But at some point here, I'll talk a little bit about minerals and mineralogy and crystals and how planets are made in that way, with the atoms, of course, that we know from the periodic table, the elements. But I thought I would talk a little bit first tonight about something that I haven't been such an astute collector going after all sorts of things with, but I've collected a few things here and there, and other samples have been given to me. And it's kind of a crossroads of mineralogy and astronomy. A couple of neat fields overlap with meteorites, because as we know, stones fall from space. And that was finally accepted as a concept about 600 years ago, and people have collected lots of meteorites since. So I thought I'd just go through a few types, try to show them to you. I don't know how well this will work, and talk a little bit about meteorites and where they come from and what they mean. I'll start with everyone's, well, not everyone's, but a lot of people. I don't know if you can see that, and if that looks like it's more or less in focus.
It looks, it looks in focus, and it has like shiny surfaces. It looks like it's got, what do they call it, thumbing or something like that on it as well.
Yeah, it's shaped a bit, and this is a small hand-sized sample of Canyon Diablo. Now, we're all familiar with Meteor Crater in Arizona, near Winslow, south east of Flagstaff there. This is a piece of the Canyon Diablo meteorite, is an iron meteorite, as you can see, iron and nickel mostly, and a few trace elements. And it fell and created about 50,000 years ago, Meteor Crater, which is the best preserved crater on Earth. It's about a mile across roughly. And as people here, we hope in the next few months, get the chance to travel around again a lot. If you haven't been to Meteor Crater, I highly suggest going there, because it's very, very cool. And there are these very good samples of Canyon Diablo that are very abundant, that you can collect. You can't collect there on the site, but you can acquire them from most. Collecting of items like this now happens from dealers, not so much in the field anymore. But this is a good example of an iron meteorite. Yeah. Now, what are meteorites? Well, there are a few sources of meteorites, but for the most part, they're pieces of asteroids, of small planetary bodies that exist in the solar system. Some of the small bodies in our solar system, of course, comets are the other type. But asteroids provide us the majority of meteorites that intersect Earth's orbit and fall down, pulled in by Earth's gravity and fall to the ground and are found. And there's several types, of course. There are iron meteorites like this one. There's stone meteorites that we'll look at. And then there's a hybrid as well. And we'll talk a little bit about what that means for a couple of moments. Well, a few years ago now, in 2013, there was a major fall that became very well known. It was in Russia, in the Urals, called Chelyabinsk. And it became very, very well known because it was captured, because everyone in Russia doesn't trust either law enforcement or insurance companies. So practically everyone in Russia has a camera in the front of their car. And you probably saw or could see on YouTube thousands of videos of this Chelyabinsk fireball coming in and exploding over this town in the Urals. This is a piece of Chelyabinsk. It has a very, very nice black fusion crust, unlike what you sort of is bandied about in the local sort of lore. Meteorites are not hot when they hit the ground. They only warm up for a very brief period, and they're cool when they land, but they do form a fusion crust. It's a black crust on the exterior, and you can see inside this sample the mineralogy a little bit of this stone meteorite, which is a piece of Chelyabinsk. Now, one of the great places when things normalize again, where you can get meteorites and minerals, is called the Tucson Gem and Mineral Show in the great city of Tucson. I was there, I think it was in 2014, the year after the Chelyabinsk fall, and all the Russian dealers were there with their samples. And this is no exaggeration, because I talked to lots of meteorite folks there. There was more Chelyabinsk meteorite in Tucson that year than there was left in Russia. So there's a fair amount of this stuff out there.
Wow.
Well, here's a very nice stone meteorite as well that has an exceptionally rich black fusion crust. I don't know if you can see that. It's called Camel Donga this fall, and it's an Australian fall. And what are stone meteorites, and what are those metallic iron nickel meteorites? Well, generally speaking, the stone meteorites like this one represent the mantles of asteroids, the outer part of asteroids. Mm-hmm. The iron meteorites represent the cores, the denser material that gravitationally was in at the core. They break up. Of course, the history of the solar system is rife with incredible numbers of collisions. Our own moon was formed by a gigantic collision. And so that produces lots and lots of scattered debris that has fallen in toward planets over time. To show you a very quick example of what you can do if you're in a special situation, which is kind of hard, but in 2011, a group with the magazine and I went to Tunisia on sort of an expedition of readers, and we went to a place called Tatooine, which meteorite collectors, now I'm not going to take these out of this little case because they're small, but these are actually bits of the Tatooine meteorite, which is an unusual meteorite fall that we found on the strewn field in Tunisia. Wow. And each collected a small number of pieces. We might not have made it back to the United States doing this, but we were with the director of the local museum at Tatooine, which is down near the Libyan border.
I thought that was where Luke Skywalker grew up on.
Yeah, they actually filmed, in Tunisia, not only a fair amount of the Star Wars stuff from time to time, but if you know the very irreverent Monty Python film, Life of Brian, that was filmed in Tunisia where we were as well. So anyway, I don't know if you can see this, but this is a stony meteorite, Tatooine, but it has a sort of a greenish cast there. And that is from iron inclusions. It's very iron rich, this meteorite. And the question of, imagine puzzles that you've tried to solve in your life. Well, the sources of meteorites, where did these meteorites actually come from that have been through dozens, hundreds, or thousands of collisions over the entire life of the solar system, 4.6 billion years, tracing where a meteorite came from its so-called parent body is beyond difficult. This is an exercise that it's just actually in its absolute infancy. But Tatooine, because of the spectra and other analyses that we can take of certain asteroids, is in a group of asteroids that's known to come from a group of meteorites that's known to come from the asteroid 4 Vesta. So these are little pieces of Vesta. It's somewhat unusual to be able to connect at this stage a meteorite with its parent body. This is also somewhat unusual. I won't take this one out as well because it's very tiny, but this was acquired from a pal of mine, Ann Black, who runs Impactica meteorites. This is a meteorite that fell in the Sudan in 2008. And you see it's a small slice of stone here. It's called Almahata Sitta. And this is very unusual because it is the first meteorite ever recovered on the ground that was imaged by a network of astronomers tracking the object and imaging it, photographing it, the Catalina Sky Survey, as it came in toward Earth before it impacted, and then also recovered on the ground. So there's an unusual one as well. Not all meteorite-related stuff are actually meteorites. They're also so-called impactites. This is a kind of a pretty version of multiple kinds of impactites. Some of them are called tektites, which are fused black or brownish glass that has been Earth material, but it's been impacted and superheated into a fusion glass, if you will. And this is kind of the prettier version of that. It's called Libyan desert glass. And this is a piece that is from, surprisingly enough, the Libyan desert. But this is impactite from a large ancient collision that superheated the sand of the Libyan desert and fused it into this so-called glass. That again is iron rich, which is giving it its yellow greenish color, comes from iron atom impurities.
David, I have to
yes, sir.
That the specimens you're showing are incredible specimens. Some of the many of us might have meteorites, but they're very kind of small and
you can get, I've been, and this is something that, you can get a nice little, Cicotaline or Campo di Cielo, beautiful little piece, iron piece that's called, for $5 or $10, that's a beautiful little meteorite. And I have seen, lunar meteorites for sale, big ones, at the Tucson show and at the Munich show in Germany for, with a listed price tag on the thing, of $587,000.
Right.
So, which is way beyond, I'm showing you fairly common stuff here, but you can get into meteorites and appreciate them in meteorite collecting at any level, at a very inexpensive level, up to an absurd level of sort of museum, collection pieces. That's a good point, Scott.
Yeah, David, is it also true that, meteorites are, an individual meteorite, the type that it is probably rarer than any diamond that you might find. Is that true?
Yeah. Diamonds they are rarer than diamonds. That's true numerically, certainly. And diamonds, of course, are very, very desired. Everyone wants diamonds. So they're more desired, even though they're much more numerous as well. So that drives the diamond market prices up, of course. But you're right, meteorites are truly intrinsically rare. Some of them, the entire main mass. So, we'll talk in a minute about that a little bit more, Scott, when I get to a couple of others. Here's another little slice, which is quite nice, of an iron. This is a so-called ataxite called Chinga from Russia. This fell it was found in 1913. We don't know what the fall date was, but you can see the iron nickel with some other impurities of rare elements as well, but it's mostly iron and about 8 or 9% nickel, perhaps. But you can see when you slice this stuff, it's like a mirror. The sort of metallic, which has been buffed, and there's the non-polished side. But this is a beautiful, sort of display. Some people even make belt buckles and stuff out of irons like this. So there's quite an interest in that kind of thing. Now, I talked about irons in the core and stony or rocky meteorites representing the mantles of asteroids. There's a composite boundary type of meteorite as well that's called a palisite, and it has iron nickel in it and also mineralogical crystals called olivine or in the jewelry trade, they call olivine peridot. You might have heard of that, of a birthstone. And its real mineralogical name now is forsterite, actually. So it has 3 names now, the crystals. But this is a really nice slice of a palisite that has those crystals in it of olivine and also the iron nickel. And this is called Esquel. It's from Argentina. I don't know, can you see the crystals of olivine in that
That's
slice?
incredible.
Oh yeah, that looks
Yellowish
awesome.
green. And this piece came from Bob Haig, the Tucson dealer who had the main mass of this sample, which he got.
Is this one of the least expensive types of meteorites?
That is, we're getting up to the really, really expensive ones now. You're right about that. Those are not cheap, and this one's even more valuable. This is called Dar Algani 400, and this is a moon rock slice. And so the best ways to get a moon rock are either to break into the Johnson Space Center and get away with one, which I do not recommend trying, or to get a meteorite that has been identified as a lunar meteorite, because the analyses of Apollo rocks enable identifying the ratios of certain isotopes of, say, oxygen, the most common one, trapped in the crystals of these meteorites and matching them to be with a lunar origin. So here is a thin slice of the largest lunar meteorite that's called Dar Algani 400. And this is a small, you can see it's about less than an inch high, but you can see, I don't know if you can see that or if it's too bright the light, but you can, there are little crystals and inclusions in that. So you can get your own moon rock, although these are fairly valuable here as well. But if you want one, go for Dar Algani 400 because it's the most abundant, and it was a Libyan fall. Then rarer yet, when, you know, Michael Bakich, my pal, who was an astronomy editor for many years and has just retired, and we're working on projects together still. Well, one time Michael and I went to Tucson and visited Bob Haig, the sort of the dean of meteorite dealers. And he opens the door and he says, hey, Dave, you know, what's going on? Catch this. And I was stunned, and so and he threw me, this was a rock about the size of 2 palms together, and that was the main mass of Zagami, which is the largest Martian meteorite in existence on Earth. He sliced about 1/3 of that rock, Zagami, which he obtained from Nigeria, and paid for his house in Tucson with that. Wow. So it is perhaps the most valuable rock, what is left of that on Earth. And this is a little slice of it that I got from Bob. So this is Martian meteorite. Now, basically this light looks kind of bright on it here. I don't know there, if I tilt it, maybe there's now it basically looks like sidewalk concrete, frankly. But again, you know, the crystallization of gases within compared to the Viking analyses of Martian rocks show that the origin of this is Mars. And so this is a small piece, but quite valuable here. And any Martian meteorite is quite rare. There are about 5 or 6 dozen lunar meteorites have been identified, and about the same number of Martian meteorites. Now, what's cool here also is that you can analyze the crystallization time and the gases and the radioactive elements within them, the crystals, and tell that this fell in 1962 in Zagami in Nigeria. About 18 kilograms of that's that, you know, 2-handed rock was recovered. And the age there is about 180 million years. So this is what this is basaltic lava from Mars that's 180 million years old. And what's even more ridiculous is that because of the crystallization analyses, you can tell that the impact on Mars that knocked it free and the travel time that it spent between Mars and Nigeria is 2.9 million years. So for nearly 3 million years, it was journeying around the inner solar system and eventually intersected with Nigeria.
Wow.
And there we go. So that's a very brief introduction that I had there to the types of and sources of meteorites, most of which are unknown, unidentified asteroids. A few of them are known asteroids, and the really rare ones are the moon and Mars.
Wow.
That's super cool.
More to come on all that stuff, and on minerals, which is how the universe makes planets, by the way, by making minerals, to come later.
That's awesome, David. That's pretty cool.
Thank you. But it's easy, again, it's easy. You know, you can get very nice, very simple specimens to get yourself some meteorite samples quite easily from many, many dealers who are out there. So I encourage you to investigate.
Awesome. Thank you, David. That was a great talk.
Thank you.
Showed us a lot of good things to check out. So, Scott, I think our schedule is now, we're in transition. So
Yeah.
do we have, is Astro Beard, do you have something to show us?
We have no live images tonight. Large clouds of hydrogen and oxygen in the H2O form. It's raining. Let's see. I do have an image I can actually share. Quick here. Okay, this one is from when I was 4 months in. So this is literally a little over a year ago. And I went totally artistic with the colors. I didn't get a good representation anyway, but this was a DSLR image taken overweighted with ED80 no flattener on Canon 90D. And I was just going back through some older DSLR images that I had because I was looking for some good data, hopefully for a certain DSLR contest that it's going to be cloudy till the cutoff date. So,
right.
Yeah. So
it was a great early effort.
That's pretty much all we got for that at the moment.
Okay, great.
But I will say that next week or the next coming couple weeks, you either might not see me or I might be outside in the dark somewhere else if the internet works good. So we'll see how that goes.
Great. Thanks. I think we're ready to move on to our main MSRO program with Dr. Myron Masuda. Myron's been a good friend of mine for several years, for almost 10 years now, I think. I can't remember exactly when we first met, but I know that you're an optometrist. You work in that field. You do quite a bit of, you've done research in the past also. So I'm going to turn it over to you, Myron, to introduce yourself a little bit and also talk about the founding of the Mark Slater Remote Observatory.
Great. Hey, thanks, Jerry. Hey, it's a pleasure to be here with everybody tonight. I am deeply privileged and honored to be a part of this group with all these famous and important people. It's really a mystery to me how I ended up getting in with this group. So I guess that Jerry had a little bit to do with that. And you know, Jerry, I can't remember exactly when we did meet. I was thinking about that. And I think it was probably years before we did MSRO, as you were in the Rappahannock Club, as I was. And we both have served as presidents, as Glenn is now. So I imagine we crossed paths a number of times, but maybe just didn't connect for whatever reason.
Right.
But I'm glad we did. We have both been very instrumental in forming MSRO. I could not have done it without Jerry's help. But to just give you a little bit of background, let me share my screen. Just got some pictures I wanted to kind of maybe bring up here. And maybe what we'll do is see if we can show here some pictures. That doesn't look like my screen. That's kind of funny. Maybe. So it says I'm screen sharing here.
Yep, we can see your screen.
Okay. So let's see then. Let me just minimize this.
You see your browser.
Yep. I'm going to get to some pictures that I've got on this. So just a quick picture of Mark Slade. Our organization is the Mark Slade Remote Observatory. And a lot of people think that I'm Mark Slade when they're contacting me via email, because it's an observatory in my backyard. And naturally, you might think that it's named after me. But I chose to name it after a friend of mine who's passed away now. Back in 2015, Mark died unexpectedly, and his wife and I and Mark were close friends, and she wanted to know what to do with all his stuff. He was getting ready to build a remote observatory in his backyard. His passion was astrophotography and sharing the sky with anybody who would want to listen to him talk about how he took pictures of galaxies and nebulas and things. And he was very passionate about trying to get young people involved in astronomy. So I thought, what better thing to do than to use his name in an observatory that was basically built in honor to promote his legacy. And we used initially his equipment that he had amassed over the course of 10 years or so to build an observatory in his backyard, which never got completed. But he had a garage filled with stuff, domes and telescopes and drive systems and cameras and more telescopes and mirrors and all kinds of cool stuff. So his wife graciously just said, Myron, you can have everything, do what you want with it. So I thought, let's build an observatory that will be used as a tool to help train other people who are interested in astronomy to use their telescopes better, or to learn techniques such as astrophotography or spectroscopy or photometry as a training institution, as well as possibly even a resource for outreach, so that local school groups with scouts or students could come over and use our telescopes to view the sky. So that was the idea, but I wanted it to be remote so that people could all over the world could use these telescopes as well. And we wanted to be able to provide these telescopes for free to people around the world. So I needed an internet connection. I needed software that would allow telescopes to be accessed. I needed screen sharing software, none of which I had really much experience with, because I'm an optometrist. I'm not really an engineer or a professional astronomer. So Jerry was the first person I thought of when at a club meeting we talked about his books that he had written on remote observatories. And I thought, what are the odds? The person that wrote this book is in our club. So I approached Jerry in 2015, late 2015, and he was on board right off the bat with this. And we both knew we had an insurmountable almost job ahead of us, because we wanted to create something that would be behind the scenes, that would work, that would not be frustration to use remotely. And that's a tall order, because there's so many millions of things, as we learned, that can go wrong with building a remote observatory. And but one by one, we overcame these obstacles. And in doing so, created what I'm really very proud of, and that's the Mark Slade Remote Observatory. And in addition to the observatory, we also managed to put together a team of amazing people that had expertise in different areas. And these people have now become members of the MSRO. We call it the MSRO Commission or MSRO Science. And we have a couple of them on tonight, Glenn and Lauren, and of course, Jerry. And I'm also privileged to have tonight with us a couple of our remote observers, Max and Alex, who we'll be talking with shortly. So let me see if I can pull up here some pictures of things of the observatory. So yeah, here we go. So that's basically MSRO right there. Okay, so it's not on a mountaintop. It's not anything that's super impressive in terms of size, but nonetheless, I think it's impressive from what it can do. And what we have are 3 separate stations. On the left-hand side, you see the domed facility in the background there. That's our original Station 1, we call it. And inside Station 1 is a Explorer Scientific 6.5 inch, 165 millimeter APO refractor on a G11 mount. under a 6-foot home dome mounted on top of a 7 by 7 foot structure. And this structure here, this station would not have been possible were it not for the generosity and importance of Explorer Scientific and Scott Roberts. He donated an immense amount of equipment to us in the form of smaller telescopes, the mount that you see here. We use computers and electronics that are just very sophisticated. We don't need to guide because we use a telescope drive master, which again was Jerry was able to secure for us as a donation. So we are able to do what we do because we were the benefactors of a number of generous people. And Scott, I wanted to say thank you for all you've done over the years for MSRO.
Thank you.
So
you guys are a great organization, and we're proud to support it.
It's been a wonderful partnership, and I look forward to it being going on forward here for many years. So that was our first station, and then I guess I could say I got obsessed and said, if 1 is good, 2 is better, and if 2 is even better, 3 is even better than that. So let's expand. Let's build more telescopes so that we can satiate the demand for all this telescope time that we're going to have, that we're giving away for free. And so I ended up building Station 2 next, which is the tan-colored blocky building you see on the right there, which is actually a mobile enclosure. I've got some other pictures of it in just a minute. I'll show you.
I want to interject real quick, Myron. I'm sorry.
Yes.
We are a nonprofit organization, so we do provide as much free time on our telescopes based on donations and things. And we donate our own time and effort into it too. So that's really what we're all about. And Myron will talk more about that with his students.
Yeah, I was just getting ready to get to that, where we are a 501c3 called MSRO Science now. So we've actually moved away from just MSRO to now MSRO Science, and we're a small 501c3 nonprofit that accepts donations of telescopes, equipment, cameras, whatever, money to help us keep doing what we're doing. And we've only been in existence as a nonprofit for just a little over a year now, but it's been a great year actually for us. So Station 2 has a 12-inch telescope in it, originally a 12-inch Schmidt-Cassegrain LX200. And that telescope is now currently being reconfigured, and we're redesigning the mount a little bit and upgrading it to the Explorer Scientific PMC-8 system. So we put another telescope in there right now, which is a 10-inch RC telescope. I've got pictures of that in just a moment. And then the third station, Station 3, started its life off as a chemical storage tank that you see in farmers' fields with a white polyethylene type of a tank there with the chemicals in it. And I took the tank out and used the exoskeleton of that as a framework to build a remote observatory enclosure that I'll give you some pictures of here in just a moment. See here. So here's the Station 2 telescope as it's currently configured. You can see we're very good at wire management. We have very good control of all of our wires and power supplies. That's, of course, a joke because that's the sloppiest telescope wiring system I've ever seen. But hey, it works. And when you get to be about 95% of the way operational, that last 5% is really hard to finish because it's working. And it's like you don't want to do anything else to mess it up. It's working, so you kind of leave it alone. At least that's been my experience here. So this is a 10-inch TPO RC that we're using right now for photometry, and this is the telescope that we've used for some of our spectroscopy and photometry that Max is going to talk about a little bit later in our program tonight. So the structure basically rolls on and off on wheels. You can see the track system at the bottom there, and it's worked great. I mean, I push it off and push it back on, and it works great. So there's a picture of it in its open position with the observatory rolled back in its operating location. And
I was asking Myron why he didn't cut a little moon crescent into the door there.
So my wife calls this the outhouse. She's got a nickname for all these observatories. So the station 1 is the hot tub because it's got the white dome over it. This one, station 2, is the outhouse. And so here's another picture of stations 2 and 3 next to each other. And we just had some snow recently, so I thought it was a pretty picture. I thought I'd take a shot of those. Here's the station 3 telescope. This is looking down into it with the roof rolled off. It's a roll-off roof structure that's been out there for a year now, and it just sits on the grass. Okay,
it's a 4 foot by 4 foot cube, right, or something like that.
Yes, it's a 4 foot by 4 foot cube. It started off as a chemical storage tank, and I took the tank out and I used that metal framework that you see as basically structure framing to screw and bolt and attach everything else to it to make this a remote observatory enclosure. And because it's palletized, meaning that, you know, it's designed to be lifted by forklift, there's holes in the bottom that allow you to slide 2x4s through, and you can take 2 people on each side and pick up this whole thing and move it around the yard if you want. If there's a position that you need it in for a certain observation, you can move it. So it's actually a mobile telescope enclosure. And it's heavy enough that once you set it down on the ground, after a day or so of settling, you can polar align, and it doesn't move. It does not shift polar alignment. And that was one thing that I was testing over the past year, was how stable is polar alignment. And we found it's really good. As you can see, we use a Explorer Scientific 102 carbon fiber apochromatic refractor and a CMOS camera here for imaging. And this is our training station. This is the one that we allow new users of the facility to log into, to get practice, get their feet wet, you know, using a remote observing. There's nothing they can break there. So, okay, so let me see if I've got anything else here real quick about that. Nope, that's it. So that's my intro to observing. And so I think right now my time is next to introduce Alex and Dave.
We got plenty of time. I think we're a little ahead of schedule. So
okay.
So Alex and Dave would be great. Talk to them.
Okay. So why don't I go ahead and introduce the 2 observers, the guest observers that we have on tonight. These are 2 gentlemen that have been using MSRO from different locations around the world. Actually, both of them are outside of the country. And we have one other guest observer who uses our telescopes from inside the country, inside the US. He's a high school student. His name is Max Domnowski, and we're going to talk to him a little bit later. So what I'd like to do now is introduce the 2 observers that have used MSRO, and then ask one of them at first to just give us a brief discussion about how he uses MSRO and what he's done with it. So up in frigid Canada right now sits David Dohaus, who lives in Thunder Bay. And Dave is a very prolific observer of variable stars and has contributed immensely to the AAVSO, and is an AAVSO observer, as well as I know he's involved with various observing alerts there as well. And about a year or 2 ago, he contacted us about MSRO and was interested in using our telescopes to supplement observing that he was doing with their Bright Star Monitor telescope network.
I think it's been almost 3 years.
It might have been, yeah. And he was using those telescopes to observe long period variable stars. And he asked if he could have some time on our telescopes, and offered to make a generous donation to our MSRO facility in the form of a star analyzer, which is a spectroscopic grating. And so he purchased that, and ended up, having it sent directly to us. And we installed it in our filter wheel, and it's now being used in our Station 2 telescope for spectroscopy, and is delivering amazing results. I mean, it's low resolution, but it kicks butt. I mean, it's amazing what you can do with low resolution spectroscopy on some of these stars.
Mhm.
So anyway, I'm going to turn this over to Dave, and then after Dave is talking, we'll introduce Alex, who is an observer he's actually living in Poland right now, I believe, but he is Greek, and he and I have developed a friendship over the past year or so, and have done some observing. So we'll see him after. We'll talk to him shortly after we get done with David. So I'm going to go ahead and unshare my screen, I guess, and then turn this over to you, David. Okay.
Yeah, I'm fine. Thanks. Okay, Jerry, you're right. It's been 3 years, I think, since I first tacked on you guys.
Right. Yes. Mm-hmm.
Yeah, the most recent one I did with variable stars was a research for Dr. Michael Stroh. He was a student at the time, and he was studying. He wanted to do studies on masers, and maser stands for the microwave amplification by stimulated emission of radiation. And we used large mirror stars to do this. And if you look at, it wasn't for masers, it would you wouldn't have microwave ovens, which were used in the first space travels, because you can't burn stuff up there, of course. And then, of course, laser is related, and it's used. It's also light wave amplification by stimulated emission of radiation, and lasers are used a lot in eye surgery. So he's doing research on this. He hasn't printed his results yet, but he also was working on using radio waves and to study titanium oxide. And I was thinking myself, maybe I should go back and get some spectrums on these particular stars, about 20 of them, and see if I can find any titanium oxide lines in there. But it's been 2 years of it. I was getting tired of it in a way, but I've been using the MSR scopes for other things. One reason is that we have a lot of LED lights put in our city now, and they're not very kind to the night sky. And Lake Superior, which is massive, didn't really freeze up this past winter, and it gave off a lot of humidity, and the night sky has not been that good. Now, my wife and I have a summer cottage inland from Thunder Bay where it's excellent night skies, but we only go out there between May and, say, September, October.
Hey,
so
Dave.
Dave,
I don't mean to interrupt you. I just wanted to see if you could maybe share your screen, because right now
you can't do it.
We can't focus on you because your screen's dark. So I guess keep the picture on me. I'm just going to sit here and nod.
I was going to try to stop it.
Yeah, mime his words.
Yeah, that's right.
I was going to do something, but I found the thing on meteorites so interesting. I didn't want to turn it off and try again. I'll do that tomorrow on my own. So we did the laser study, and hopefully he has all the data. And the images that I got from your scope were so good, and the readings were so accurate. I don't want to put down AFSA, but I was using the Bright Star monitors, which are small telescopes. But it's been an opening for me to do more studies, and that's what I like about your facilities. So I will continue to try to do that. But some other things, back to the masers, it's based upon, I guess the theory is based upon quantum mechanics. And I took my degree in mechanical engineering, which is based upon Newtonian mechanics. But I do have a 3-year diploma university certificate from the University of Lancashire. So I know a little bit about the quantum mechanics of astronomy. And I did a lot of stuff on astrophysics of galaxies. Your stories on Nigeria are interesting because I did come back myself with some bits of meteorites found on the Sahara. And I'm going to go back one more step about my experience with astronomy. I learned to fly an airplane when I was 17 years old through an Air Force scholarship. And in Ontario, here in Canada, we had to go to grade 13, 5 years high school. So a lot of us who came from, families that didn't have all kinds of money, we tried for all the scholarships we could, and we're fairly successful. But my dad taught me where the North Star was. And I had to fly out to Sulikau, 200 miles away, and I got into some terrible headwinds on the way out, late afternoon start. And on the way back, I had more headwinds. It just all reversed. my dad taught me who the North Star was, so I lifted the wing of my little Aeronca. Jerry might appreciate this because he's a pilot. Yeah. And I saw the North Star. Then I kind of tried to make allowance. I didn't know much about how fast these stars are moving and the Earth spinning, being 17 years old. But I found a star that I followed into town 200 miles away and made a landing in a very, I lost all my electrical lights on the way in. But the stars got me home and I made a very safe landing. So I'll never forget that night. So that made me get interested in astronomy. In fact, when we lived in Nigeria, I'd get very homesick because the North Star and just the top of the Big Dipper would be just on the northern horizon. But this got me really into astronomy, and I do all kinds of other things, but long-term variables are on the agenda now, but it'll change. I'll just start doing something else. And our son's a dentist here in Thunder Bay, and he was born here, but he grew up in Nigeria for a few years. But he's doing some really great astrophotography. And I have to outdo him. I might try some of that with your equipment. So anyways, I'm so happy to be able to use your telescopes. And it's opened up a lot of doors for me. Keeps me out of the coffee shop with my crony friends who talk about I coulda, woulda, shoulda. And I said, I'm not listening to you guys. I'll see you during golf season, but don't phone me in the wintertime because I'm not going out for coffee. I'm doing too much astronomy, which takes up a lot of my time. My wife seems happy with that. So hats off to you people for doing what you're doing for the public. And I really do appreciate what you're doing. And I think that's all I could go on forever about this stuff, but I won't. So, because I found your first talk already very, very interesting. So I'm going to sign off for now and say a big thanks. Thank you.
Thank you, David. I appreciate that. It was very nice seeing you on here tonight. I know you're pressed for time and you were telling me that you might be able to, or you might have to leave us. And I just want to say thank you again for joining us and I appreciate you being here.
Okay, thank you.
Yeah, thank you. So at this point, I'd like to introduce Alex, who is another observer who's using our telescopes. We have talked off and on for the past year and a half or so. Initially met through our Facebook page, the Mark Slater Remote Observatory Facebook page, which is where we post a lot of our images and our results, you know, the observations that we're making, cool pictures that we're doing, exoplanet light curves that Jerry obtains, and all that goes on our Facebook page. So it's something I would encourage you all to look at from time to time if you'd like to see what we're doing. It stays pretty fresh. But I met Alex there, and he sent me some private messages along the way saying, hey, I'd like to see if we could maybe do some collaborative work together. And next thing you know, we're observing stars like X Persei or EE Cepheid. And so I'd like to just turn it over to Alex for just a few minutes, if he could tell us a little bit about what he does and a little bit about himself. And that would be great. So Alex, the floor is yours.
Hello, everyone. It's the second time I'm attending a meeting. It's nice, and I want to thank that I've been given the opportunity to participate in this big effort of observing with these observatories. When I first saw in the Facebook page, I was surprised in a nice way, because it's not very often that you see some amateurs working with photometric filters and with spectrographs or prisms. And that's what really made me curious. So I'm a PhD student in astronomy. I have worked on X-ray analysis with data. And actually it is quite easy to find data from satellites, X-ray and gamma ray, of, let's say, stars that have accretion disks around them. And these disks are so hot that they emit in X and gamma rays. So you have satellites for X-rays. If you get lucky, you can find data for radio data, but it's difficult to find optical data. And that's where it gets interesting for us, because the observations that I've been doing with observatories about pro-am collaborations. So quite often I learn about campaigns like EE-Cepheid or X Persei, where people want amateur astronomers to give photometric data. It's something simple that everyone can participate. The stars are quite bright for this task that they want to do. For example, I think spectroscopically, the first thing most people start observing are BE stars. So these are stars of the B type, spectral type, but for some reason they emit sometimes hydrogen. The most famous and the first one that was discovered was gamma in Cassiopeia. So that's in the middle one, the nose of the Cassiopeia, in the W. And the idea is that there is a disk around them, a decretion disk. So this disk is being emitted away from the star. And they're still quite a mystery. So with the star analyzer, we're monitoring such stars. Like the X per site has a pulsar and an accretion disk around it. And this gives valuable information, the photometric, especially the infrared band, which is good for the dust and the accretion disk. So we can, as amateurs, we can provide photometric data, optical, and we can look for correlations with data from satellites. And this is really something simple. And currently we are participating in a campaign with the ECFI, where some astronomers in Poland, they want infrared photometric data. There is some eclipse happening and there is a disk involved. And right now they are trying to understand the geometry of the disk. And this campaign will go on until June or July. So hopefully after that, the analysis will start. We will provide the data. And yeah, we will be hopefully in some publications. And this whole effort of observing and performing, giving freely time for observations will be more popular and advertised. I have to say that I feel bad because Myron is always watching me, and this is good, but I feel bad because I know he's awake because of me. There are moments that he got to go outside and physically fix something or put some cable back. And he was writing to me, now it's okay. Or he just sometimes checks, are you okay? Is everything fine? And I said, yes, please go to sleep. I feel bad. But it's also nice to know that someone is watching an all-seeing eye. Yeah. And there's always the fear of breaking something because, you know, there's a lot of effort. So you feel bad if you will be the one who broke something. But if anyone is interested to try, I would say that it's foolproof because of the effort that you guys have put there. So I want to thank you once more.
Thank you, Alex. It's my privilege to be able to go out at 2 in the morning or 3 in the morning and plug and unplug a USB cable because that's what I do. That's my job. That's why I'm the director. That's my job description, right? So quick question for you. The ECFI, there was an eclipse recently in that, and now we're post-eclipse, aren't we? Are we not out of the eclipse and now we're like just watching to see any after effects as the disk moves away?
Yeah, that's why it is more interesting now in the infrared because of the disk. So this is dust,
right?
And you have to see how much extended it is, what is the angle, and how it is moving compared to the star.
Right, interesting.
So there's a lot of geometry happening, and that's why the infrared now is happening.
Yeah, that's why we're using.
We see more of it.
That's why we're using the I band filter, right?
Yeah, exactly.
Right.
Exactly.
Gotcha. Very interesting. You know, you mentioned accretion disk, and that's going to be a hot topic of the next guest speaker that we're going to bring on in a little while. The high school student I'm working with, Max. He did a study on RR arrays, which of course aren't accretion disk stars. But after his project finished up, he was very interested in photometry and wanted to know what's the next kind of star he can look at and do, practice his skills. So we turned to cataclysmic variables and UGEM in particular, which of course is a very interesting star that has an accretion disk around it from, the mass transfer going on. So we'll be talking about that shortly as well.
Nice. Yeah, accretion disks are always a nice topic.
They're very cool. They're very cool. Yes.
in multi-wavelength.
Yes, definitely. Well, listen, thank you for your time and thank you for joining us tonight. I see it's 3:10 in the morning where you are right now. So you need to get to sleep, my friend.
Okay, so thanks for having me. Goodbye, everyone.
All right. Good night.
Good night, Alex. Thanks a lot for coming on.
Good night.
All right.
Okay, Jerry, that's all I have now until the next segment for me, which will be my the high school student that I'm working with, Max Dubnowski, which I think you have me scheduled. He and I starting at like 11.
Well, it may be a little faster. We're a little bit ahead of schedule, which is
Okay.
fine. I mean, it's great. I don't know if does anybody have any questions for Myron in terms of the MSRO, or for me even, if you like. Do you have any comments or questions out there?
Yeah, there are comments. You know, mostly complimentary comments. People commenting on Dave Eicher's talk about meteorites, the meteorites that they own and marvel at.
It looks like Dave Dowhouse has shared a screen for some reason.
I'm trying to get my picture on there,
Oh, okay.
but I'm not succeeding.
No, it doesn't. You shared your screen instead of your camera is what you've done.
Looks like you got a nice specter on there of something.
Yeah.
That's from your telescope, whatever it is.
Yeah.
Sorry about that.
It's not Vega.
No.
Oh, you know what that is? You know what that is? That's those protostars we were watching in Auriga.
Oh, okay. Yeah.
AB Auriga, is that right? Or AB and AE or something like that.
Okay. Yeah.
That was one of the protostar projects you were doing.
Okay, should I keep trying? Am I bothering you by this or what? Should I get off of it?
If you could tell us before you share your screen, that would be good. If you could not share it right now, that'd be awesome.
Okay. I'm gone. Okay, I've got you back.
Yeah, that's good.
You still have me?
Yep. Well, we see you don't have a camera on, so we don't see you. We see your
Yeah, I've got to turn the whole computer off to get the camera up, I think.
Yeah.
I'll just leave it?
Yeah, just leave it. That's fine.
Yep.
What are you seeing now? Am I bothering anything?
No.
I see you.
Yeah, that's fine. Yeah, I'm
Okay.
the focus right now. That's
Okay.
right. All right. Well, I think we're ready for a break, Scott, unless you want to go ahead, and we can bring Carol Orge on early before the break.
I think there's time to bring Carol on, and we could do the Astronomical League door prize portion. And I know Carol's been waiting there patiently. So,
hello, everybody. Interesting program so far, and I'll jump right into our questions that were asked at the last Star Party, and then add the ones for tonight's. So let me share my screen. And let's see here. Are we seeing them yet?
Not yet.
Okay. I'm also an amateur at this at times. Okay.
So you just go down, go to the bottom of the Zoom application. You'll see a green share screen button. You click on that, and then you click on the window that you want to share, and then you hit share again, and it'll start sharing that one.
All right, now let's see here. Okay, I'm sharing my screen.
Not yet.
Have we got it now?
Not yet.
Okay. Going to my desktop, which has my PowerPoint there. And I think what I'll go ahead and do is just wing it on these because for some
Okay.
reason it's not coming up. Okay. First thing we do on these is flash our warning screen for solar observing. Know that sometimes when we have the prizes, it will be an eyepiece or something comparable. And so we want to make sure that we give everybody a reminder that do not look through eyepieces without the proper filtering. And then we're going to start a new process on April 6th. We will continue to ask and answer questions, but we will not announce winners each week. We'll be awarding prizes at the end of the month and grand prizes twice a year. And then we'll have twice a year, we'll have grand prize awardings. And now we get into the questions from the last Global Star Party. Question 1, the only bright planet in the early evening sky over the next 2 months is Mars. For a couple of weeks every 2 years, including one from tonight through early next week, the red planet slides between two prominent star clusters. What are the two clusters? There were 3 options given. A was Beehive and Coma Berenice's open cluster. Option B was M8 and M20. And C was Pleiades and Hyades. And the answer was Pleiades and Hyades. The answer was Eduardo Simoni. Question number 2. With his spiffy new telescope, Galileo observed many so-called nebulae, some of which we no longer recognize as being nebula. In particular, we call one Nebulosa Aurorialis or Anais. What do we call it today? Trapezium stars, Lambda Orionis, and surrounding stars, or M42/M43? The answer was Lambda Orionis. It is also called Head of Orion Cluster, an attractive binocular object. The winner on that one was John Pershilly. Question number 3 from last Star Party. About how many volunteers does this Astronomical League have who contribute to the operations of the organization, making it a success? 100 or more, the 5 members of the National Council, 10, 1 from each of the 10 regions, and the answer is 100 or more. The winner was Laurie Ansorge. And now the questions for tonight's Star Party, number 37. Question number 1. In what constellation do we find the star Betelgeuse? I'll repeat that. In what constellation do we find the star Betelgeuse? And the answer should be sent to explorealliance@explorescientific.com. And Scott, if you could put that in chat since I'm having difficulty showing my screen.
Yeah, I got it.
Excellent. So that's number 1. Number 2, what is the name of the path that the sun, moon, and planets take across the sky as seen from Earth? I'll repeat that. What is the name of the path that the sun, moon, and planets take across the sky as seen from Earth? Then number 3 is, what are the names of the 2 stars in the bowl of the Big Dipper that point to the star Polaris? Question number 3 again. What are the names of the 2 stars in the bowl of the Big Dipper that point to the star Polaris? And again, those answers are sent to explorealliance@explorescientific.com. And one thing I've just mentioned very quickly is that we just recently announced that our national convention, Alcon, has gone virtual for 2021, and more information will be coming in August. And now back to you, Scott.
Okay, all right. And we are going to take a 10-minute break right now. Be a good time to grab a sandwich or a hot drink or something like that. And we'll see you in a few moments. And if you have, if you're really enjoying this program, please like, share, subscribe, and click that little bell if you're on YouTube. We've had a nice lineup of speakers already. It's been great.
Scott, what was the address on those graphics that you introduced at the first?
What was the address of the graphics?
Yeah, from NASA. There was a link or something, wasn't there?
Oh, yeah. Here, I'll send it to you.
Those are very cool.
Yeah, they are cool. And, you know, both NASA and the ESA go through great effort to put these things together, and they're designed for outreach.
Yeah.
Let's see. Here's one. I'll go ahead and put it in the chat, and I'll send it to you too. If I can do that right now. Here you go. That is from the Goddard Space Flight Center. Some of their visualization things that they do.
Excellent. I see it there. Wonderful. I appreciate it.
And there's an ESA one that I use as well, and they're doing a great job.
Yeah, those are most impressive. They are very attention getting, which is what we want to do in outreach.
Sure. Very informative. You know, there's historical ones, and then there are, of course, ones with some of the very latest findings in science, you know. There you go.
Yeah, excellent. Thank you.
Mm-hmm. And I'll put that one in chat as well. John Paris Chili is asking, Scott, I was interested in the spectrograph that the guys in your first guess were using to collect the data, and which telescope were they using? Both Myron and Jerry seem to be getting a sandwich right now, so we'll get that answer when they come back, John. Okay, but I think they're just using a grating, and probably the spectra they're collecting might be through the ED-165 Explorer Scientific refractor. But it can be done with a lot of different telescopes. And there is a software program by Tom Fields called RSpec. And let me get you that address. This guy's really led the charge for amateur spectroscopy. We'll have to have him on our show sometime. He's a fantastic speaker.
Looks like time is getting short. We got 30
Yeah.
seconds.
30 seconds. If you're having tough time reaching the YouTube channel, I just posted it up there. It is live, so Pekka couldn't find it for some reason. John Parastilli says, thanks, Scott. I'm just amazed at what can be done with amateur equipment and especially collaboration across the globe. That's true. We have the power.
That's right. We have the technology.
We have the technology.
Fortunately, it's not $6
For
million.
amateur astronomers, we could do anything.
That's right. Yeah, we can build $6 million worth of technology for 50 cents. For 50 cents.
That's true. Well, okay, so we've got a number of our people back with us here after our break. Jerry, I'm going to hand this back over to you. And up next is Libby and the Stars.
Libby and the Stars. Hi,
Yeah.
Libby. How are you?
Good. How are you guys?
Good. What are you going to talk to us about tonight?
So I have plans to talk about life out in the universe.
Life out in the universe. That's awesome.
Yes. Let me pull up what I have. So let me present my screen.
All right, good. Thank you. Thanks for being here. I know you've tried to come to all these global star parties. It's awesome what you're doing.
I very much enjoy coming here. It's very fun.
She's been at every one so far.
Wow. Awesome.
So life in our universe, people might question it as aliens and stuff. So the question always wonders, because I know a lot of people always ask other people, like, do you believe in aliens when you're talking about space? Because like all over the world, aliens are probably one of the most mentioned things. If you're going to talk about space, people are always going to ask you, do you believe in aliens? And I mean, we're in a generation that I think we'll find out soon if there's, not aliens. I know a lot of people on like TV and stuff, they broadcast it as like little green creatures and stuff. But I think we're in the generation to find out like what life is out there in the universe. Now, I don't believe in the little green creatures, but I do believe there's like tiny little biological life out there that might be like little molecules or something. Maybe like plants or something. I mean, not something that's really living, but just that's what I believe in. I know aliens are advertised a lot, and many people have different ideas of what aliens look like. And when I say aliens, I don't mean the little green creatures like I keep on saying. They're just life out there in total. People have many different ideas. Now, a lot of people don't believe that there's any life out there. And I believe there might be plants out there. I mean, I don't think there's life, but plants out there, they can breathe oxygen. Because number one, our universe is expanding almost every hour, minute, second, and we don't even know how big our universe is or when it ends, and like all of that stuff. So I mean, the question is like, some planet could be like Earth and just have plants. That's mostly what I believe in, just plants. On TV, I know they broadcast a lot of shows about like aliens and stuff, and people taking videos online and posting them of like little airplanes flying by that they might have mistaken for a UFO coming to attack their civilization. And it's sort of crazy because like a lot of people out there will take videos of their cell phone and they'll post it all over the web, will become famous and everything. And usually those always get debunked because they're always like, yeah, that was not true. That was actually a plane coming by. That plane was a jet plane shaped differently or something, or sometimes fireworks or a comet coming by and a meteor shower. Sometimes people video it and think that it is an alien. And I don't think that those videos are very true. I do believe there might be plants out there on another planet, but I don't think there will be any other humans. And also our generation, we're making progress on exploring space every single day. NASA, they've picked back up on a lot of the space stuff. We just landed another rover onto Mars and started exploring, and that's like, and NASA's question right now is finding out if there was ever water on Mars. And so I remember once when I was back at space camping a long time ago, a year ago, we were talking about life on Mars because basically, like, if there's water, possibly could grow moss or plants underwater. And if Mars ever had water, that could have happened. And plants give off air. So, I mean, we were thinking about it not as there were aliens out there, which we totally weren't thinking about that. We were thinking about the question of, like, could humans live out there? Because I know NASA has been trying to find other planets humans can live on. And I think that planets that have water that can grow, plants and a bunch of trees and stuff that give off oxygen would be an important piece of information to remember when you're looking at research about Mars. And yeah, I was just talking about Mars, because NASA is trying to go back. And a lot of theories say that Mars used to be like Earth. And that's NASA's main point right now, is a lot of the searching on Mars and being the first people on Mars, and knowing if Mars was ever just like Earth once and all the water just left, and there's ever water on there, taking samples back to back all the way back to Earth, and being able to see if there's like any water in them. And they've been on that hunt for a while now, and I think it's nice to live in a generation that will finally find out if we can live on any other planet, or we can live any other place in the whole entire solar system, space, even our universe, if we get there one day. Oh my gosh, my mouse. Oh, well, anyway, my presentation just loaded out, so let me get back to where I was. I guess it loaded me out, but yeah, left click, not right click, that will load you out. Lesson learned. And like planets all into the whole entire universe. That's our generation's purpose right now, is to find another planet to live on, because honestly, going back to a long time ago when it was a space race, all of our goals were to, you know, find another place to live on different planets, like sci-fi movies, and be able to fulfill that dream. And some people were even like thinking like befriending an alien. Like people wanted to live on different planets of aliens. I don't think aliens are like sort of real. I mean, plants on other planets, but they give off oxygen. And if humans could survive on different planets, I feel NASA's going to definitely want to look there. And I feel there's a special urge that other, like everybody, like looking for, everybody has different ideas on aliens and taking over our universe and conquering space, because that was the first idea of the space race, was whoever could conquer, you know, being the first person out in space, being the first person on the moon. And I feel that competition is going to go on forever, because the universe is never ending. And soon enough, one day, we'll find a planet with lots of nice conditions, and maybe even like plants, because plants are practically alive. Even find plants on other planets and start a whole new planet Earth, like not even living on our own planet, just starting a whole new planet Earth and conquering the whole space universe, and finding out if there will ever be life out there. So I like to say, don't right click. The question remains unsolved. Sadly, I can't answer the question if there's ever life out there in the universe right now, but because I don't know that, not even NASA knows that, not even the whole entire world knows that right now. But a lot of people have opinions on what is out in space, and I definitely think there might be plants on another planet, but I'm not sure about the alien side. I'm sure that one day we'll be able to find a planet that has some sort of life on the planet, and be able to conquer that planet and be able to live on that planet and be the new space frontier. I'm going to stop sharing. Here we go.
Thank you, Libby. That was great.
Thank you.
That was a good talk.
You know, Libby, if you went to the Jet Propulsion Laboratory and you talked to the scientists there, and you ask people that are, I mean, seriously involved in planetary exploration, do they think that there's life elsewhere in our solar system? You will get a very sober, affirmative answer. Yeah, yes, we do think that there's life elsewhere out there. And that's why we're spending our lives and the effort and the money to try to find out. And so it is one of the most important questions in all of humanity. And probably you've got a good chance within your lifetime to see it happen. So I'm glad you're paying attention to it.
Thank you. I think the conversation could go on for hours of whether aliens are real or not. Usually, like some of me and my astronomy friends from like space camp, we'll spend hours emailing each other on whether like aliens are real or like plants on other planets real or anything about space, and we'll just spend hours sharing opinions on the new space frontier and conquering it all.
Yes, I think eventually that the way that we would call other life in our solar system aliens, I think that might change at one point, because the human species is a spacefaring species now. We are 24/7 in space. We're on the International Space Station. We have dozens of spacecraft all over our solar system. And we've got a couple of spacecraft and a third one heading out towards interstellar space right now. So we don't just inhabit this planet. We are a spacefaring species. And so, if bacteria could somehow recognize us or see us as another living entity on Mars, they would definitely call us aliens.
Right. All right, cool. So next we have Glenn Faini, the president of the Rappahannock Astronomy Club. He wants to talk a little bit about our club and what we do in the Fredericksburg area in Virginia. So I live in a town called Locust Grove, Virginia. We have a club that is in, I guess you would call it, it's halfway between Richmond and Washington, D.C., if you're not familiar with Virginia or where we're at. Fredericksburg is a very historic city in the Revolutionary War and also during the Civil War. So we're in a very historic city, but we have a great club also, and Glenn's going to talk about it a little bit in our membership and what we do. Thanks, Glenn.
Well, thank you, Jerry. First, I just want to say I'm honored to be included with such esteemed scientists tonight. I am the current president of RAC. I'm in my third term. I learned about the club, I think it was in 2004. Happenstance, I went to see my eye doctor in Fredericksburg, who was Myron. And while I was waiting, I saw all kinds of neat astro photos hanging on his wall, and I asked him about them, and he explained that he was the president of the club and invited me to join, and I went to the meetings, and I've been a member ever since. So thanks to Myron, I'm in the club. It's a modest club, about 50 members. We serve the Fredericksburg area and surrounding counties of Stafford, Spotsylvania, and King George. Some benefits, we have a newsletter that we're very proud of. We have an email discussion group. We have an equipment inventory that we maintain that can be lent to members who don't have a scope yet, trying to get a feel for what kind of equipment they might want. We have star parties. Unfortunately, right now, they're only for members. We're not doing any in-person public outreach. We haven't for about a year now, unfortunately. Right. Star parties right now are just for members. And another benefit of our membership is you get some MSRO time. We have an account of time log that
yes,
that members can use. Right, as I said, right now we're not doing much in-person stuff. we've had a few star parties. We have 2 sites, one Belmont Observatory down in Spotsylvania, and another, the public star parties are held out at Caledonia State Park in King George. Two nice border level 4 relatively dark skies for the area. We have a nice online community. We discuss stuff. A lot of discussion has to do with astrophotography. We have quite a few members who are very into astrophotography, and
I
there's
think
some fairly impressive images.
Yeah, I think one of the things that sets our club apart too is that we have quite a few members over the years that worked at Dahlgren Naval Surface Weapons Laboratory. So we have retired scientists and engineers that are in our club. So I think pound for pound, with our low membership numbers, we have quite an esteemed group of people that are very knowledgeable about a whole lot of different things. And I want to mention in particular Dr. Bart Ballard, who's a member of MSRO Science. He's on our staff. He's a retired physicist. And of course, we have Lauren, which I'll be talking to here in a minute. But first, we're going to hear, do you have anything else?
No, I was just going to end with the only other thing I was going to mention was that, as Myron had said, the MSRO started out as a project of Myron's and yours. It was actually, I guess it was sort of part of the club when it started out, but it's I guess you would call spun off into its own independent corporation, and it's getting bigger and better every day, thanks to the hard work put in by Myron and Jerry and others.
I want to thank the Rappahannock Astronomy Club for so we get a yearly part of the dues that get paid to the Rappahannock Astronomy Club go towards the MSRO, which is very generous. And then initially, when we built the observatory in 2015, the RAC Club donated $1,000 towards a skirt that goes underneath the dome on the Station 1. We needed that desperately, and they stepped up and donated money for that. So they're very instrumental in getting the observatory running. So I want to thank them again, the members of the Rappahannock Astronomy Club, for that.
And I just put the link to the club up on the chat. Give the site a look, and if you're in the area, consider joining.
Yeah, and take a good look at our newsletter. Linda Ballard is a newsletter editor. She does an excellent job. She's a professional editor and writer, and she's actually the co-author on my second book, Remote Observatories for Amateur Astronomers. But she does an excellent job with the newsletter, and it's every quarter it comes out. We got 6 or 7 years of, I guess it's more than that now, maybe 8 years of newsletters now. It's quite a body of work now. That so if anything, if you go to the website, if you're going to look at anything, go to the newsletters and start looking at those, and you'll see what kind of caliber of work that we do at the club. All right.
Excellent.
So next, I want to introduce Cesar, Augustin, and Rodrigo. I don't see their pictures up. I don't know if they're, I guess Cesar's up. I see Cesar. How you doing, Cesar?
Yeah, Augustin is logged in, and so is Rodrigo. Their cameras are not on.
The cameras aren't on right now. Yeah.
But you can go to Cesar first,
Hi, good night. How are you? How are you, Sherry?
Good. I'm great. I appreciate you coming on.
Yeah, it's a rainy night. It's cloudy night here in Buenos Aires. I am more for talking about optics than astrophotography. I can I can talk about my newest experience this week because I use it. I start to use and learning to the people to use typical astronomical eyepieces for their own microscopes. Exists an old generation of vintage and maybe some new microscopes from different brands that many people have with malfunctions or don't use anymore. Maybe you know that only use a screen and a camera inside. And in our laboratory, we started to receive for repair the models with the screens, and the people told us that they said, okay, but you don't have another option because we need a closed system where we have a camera that maybe is not the best camera to take a picture or other screen. Okay, is the style touching screen, but we started in the last time to change the system of this telescope. I'll show you what kind of telescope is. Maybe do you in many brands do you have normally here with a screen this model?
Look at that.
But we started to change the original system, making a tower with many options, and the people love it. And we in our laboratory we start to make a new tower, calculate the focal plate, the focal distance of the objectives, the best size for this, the diameter, and we obtain an excellent new tower that we can give to our customers the option to use the old ones size of eyepiece, but the new ones 125 inches, for example, like this. But this is the of course that we thought more in put a reflex camera or a camera for a planet camera, and here we have a M42 size of screw for the tail rings for to put a Canon or Nikon DSLR cameras. But this week I have one of these in my home. Of course, I keep one of this in my home, and I never tried with the 82 line, 82 degrees field of view eyepieces. Come on, the experience was amazing. So that it's only that if you can, Scott, you can if maybe you have in your laboratory to I
love it.
It's something because when you start to use for microscopy 82 field of view degrees, field of view, the experience is amazing. For example, this is when is it the 14 is my typical one of my favorites eyepiece for astronomy is 14 millimeters, 82 series degrees. And when I tried in my microscopy, the was amazing because all field you don't lose the magnification, but you really feel immersed in another cosmic place that is the microscopic world. I really enjoy normally to see, you know, open clusters with or nebulas in very nice place, dark skies, or maybe sometimes here in the city. But when I go to the west part in the mountains in Argentina or in the desert, and but I never suspect that it's so amazing the view with the 80 with a great field eyepieces to use in microscopy. And I found that the quality in the borders of the image is excellent. It's really, really nice. It's something to study, to improve more, and of course use more this type of things, changing, especially for cloudy nights. And because, you know, sometimes in cloudy nights we are making astrophotography in the computer. Or if not, you can use a microscope with your eyepieces and enjoy the microscope world. Is the possibility of optics are really it's a really wide field of possibilities, and this is one of this that for me was an excellent and a great surprise.
Wonderful.
Thank you.
I can hardly wait to try it myself, so that's great.
Of course, yes.
Yeah, that's pretty cool. Yeah.
I can give you a draw of the piece. No problem. Just because I love experiment with optics and mechanics, and really this is something like I know that it's a little outside of astronomy, but the science is technical, and really I am optician, and it's impossible to me stop to talk about optics.
Cesar, we need to get you with Myron, get you and him together, because Myron's an optician, of course. He's got training and all that. So I'm sure Myron would like to talk to you about some things.
That is an amazing idea. I mean, I'm sitting here just thinking, why hasn't this been done before this? And I was thinking also, Scott, you need to get Explorer Scientific to start selling those things. I bet they would sell like hotcakes.
I think so.
Yeah. Yeah.
Well, I've got a bunch of eyepieces that might be used on it. So wonderful. Cesar, thank you so much for showing us that. That's great.
Thank you.
It looks like Augustine is back.
All right.
Yeah,
So,
here I am.
Yeah. What'd you like to talk about?
How are you? Now,
Nice. I'm doing fine.
Augustine is Cesar's son, and he has. We introduced him a little bit on I think it was the last Global Star Party that he was on, and he gave a great talk about image processing and how calibration frames are so important. And I know that you enjoy astrophotography, and you're quite knowledgeable about it, image processing. What do you have for us tonight, Augustine?
Okay, so the image processing world in general is a really big pool of things. But I mean, you told me you want me to kind of explain noise reduction. So the thing is it's kind of simple, because it's either you look at the algorithms, or you just look at the program and which buttons to press. So the thing is, do you have like something else a little more general about it that you want me to?
Yeah, just go ahead and talk more about image processing.
Okay, yeah, in general, yeah,
sure.
Okay, so the last time, as Scott said, the last time I talked, I was talking about why the whys and hows of calibration frames, which are not only in the casual hobby situation, like, yeah, I'm gonna take a photo of Andromeda and I want to do it like correctly. Yes, that exists, because that's what most people in the astrophotography hobby world do. And yeah, I also compare it to the scientific side, which is actual precise data, which you wouldn't be able to have if you don't apply those calibration frames. So it's not really much to talk about in a specific way of each process, but maybe I can like give a fast idea of all of the processes you can use and what you should use. So I'm gonna share my screen. I'm gonna share PixInsight. It's already open. So here, if you can see, it's a very old picture I took with my dad of the Helix Nebula. I wanted to find some individual frames, but I couldn't because, as you know, when you don't have like the perfect year and the perfect sky, you end up taking way too many individual frames. So I had like a 100 gigabyte folder of only individual frames. So I kind of deleted them all and I just kept the final stacked image. But the thing is, what I wanted to talk about is a really fast and important thing to do is noise reduction, because even when you stack the images, there's a little leftover that you get even when applying the dark calibration frame. So for the PixInsight users, which I suggest is like what you should use. I know the license is kind of expensive, but that's the way to go. I'm gonna use the same image because I was doing a test with that image. Where is the thing? So one thing I've seen with people that people do when reducing noise, there's this like order of things you can have, which is when you're using PixInsight, when you open your stacked image, you will see that the image it's all gray or like all black. First, you shouldn't have to worry. I mean, if you know this, what you do is you stretch the image, and stretching means that you're gonna rise all the information. Let me check because I can't find the image. And what it does, there's a process for that. I'm gonna show you in a second. What it does is just makes all the information in a smaller passage. I'm gonna show you in a second. Okay, so okay, I'm just gonna grab a random one because I can't find the Helix one. Okay, so in this example, this is the Magellanic Cloud, the major one and the small one. So if I do a zoom in, maybe you can see the blue, red, and green cloud of pixels.
Yes.
Right? Okay. So in this case, the image it's already stretched, but in the way you're gonna see it right after you stretched it, it's gonna be something like this. Right? All black. Oh, wait. So what you do is the opposite of what I'm doing. You grab, in PixInsight, you grab the process called histogram transformation, and you take the middle point up and do some cut of the low point. What this will do is stretch. I mean, this is called stretching the data, and will bring up all the information. So why did I talk about this? Because there's people that do noise reduction after stretching the image, and there's a difference, but I mean it's very little. For the naked eye, it's like you don't even notice. But the thing is, for a specific objective of an image analysis, that type of order that you use, it will ruin the whole information, like the average of the information you have. So the best to do is doing noise reduction before the stretching, because if you don't do noise reduction before, when you stretch, you're also stretching the noise. Because it's logical. You just have it there. You didn't remove it. I mean, you never remove it completely, but you're gonna rise all that that erroneous data, like that that information which is on top of the useful information. So what you do is noise reduction before. This image is already stretched, so I'm just gonna do noise reduction because I couldn't find the unstretched version of this one. And the important thing of this is I just wanna explain how this particular process works. The order is just so you know when you're doing it. Just remember that it goes before, and what you do is in PixInsight there's this process called STF, which is Screen Transfer Function, which will auto stretch the image, but it won't apply it. It will show you a preview. And well, you just reset the thing and it will go back to the actual state. So I'm going to show you how this works. And I want to do an explanation, which is very important because it will give you like an insight of how the program detects noise. So in this case, you see this window that says layer 1, scale 1, these random numbers. Okay, at first they look like random numbers, right? But they mean something. The layer, well, is just a layer. And the scale, which is the important part of this program, is here it says scale 1, 2, 4, 8, and 16. What this means is that the image will calculate the pixels in sizes of that scale. So if you have scale 1, that's a 1:1 scale of the image, right? It's the actual size of the pixel. Now, if you have scale number 2, that means that the algorithm will take in account a 2:2 size of a pixel.
Mm-hmm.
So that means half the information. So a more blurry version of the image. And you can see this using a script, which is they are very useful. The scripts, they help a lot for image analysis. I mean, the script is called image analysis. This is called wavelet layers because this is what it's about. It's about wavelet layers. Okay, I'm gonna match the plugins. So this uses the scaling function is a linear interpolation, right? And it uses 4 layers. So I'm gonna use the same 4 layers and linear interpolation, right? and this will extract the wavelets, those 4 layers of this said image. And you will see what type of noise is in which layer. So, for example, here in layer 0, which should be the layer 1, the pixel size 1 by 1, there's a noticeable amount, but not that high. I mean, you should always remove whatever you see in the best, like fiddling with the numbers the best possible. But yeah, this will give you an idea of which layers to apply the most reduction. So here, layer 1, I mean, because the perm starts counting at 0, that's the layer 1, it's the layer 0. There's some noise. Here you can see the star. Okay, let's go to the layer number 2, the 0, 1. Here you can see a lower resolution, quote unquote, and the stars. See how you can start to notice some paths between the pixels? That's because of the lower resolution, because of the bigger scale. Okay, so here you can start to notice more color than the previous one. I mean, it's logical because if you have a bigger scale of pixels, you will notice better the average of all colors of all the pixels. So here is the scale 2 by 2. And here is a scale 3 by 3. As you can see, it's even a bigger scale, so lower resolution. See, this one has more color than actual individual pixel noise, right? So what you would do in this case, knowing that this exists, is in the previous scales, which had a high individual pixel noise, you will do a luminance reduction, which is brightness. And then in the bigger scales, you can do chrominance. Chrominance means color. So you're gonna reduce color in the bigger scale and then luminance, so brightness, in the smaller scale, right? Because that's what we just saw. I mean, we are seeing it right now. And in the larger scale, it's just horrible because it's just like the whole average of all pixels, which I don't really take in account. So now we have a better idea of how we should do noise reduction. So I'm gonna make a mask for this photo, something that you should always use, because if you're gonna do noise reduction, you want to do noise reduction on the background, right? Because in the stars, you actually have a very high signal to noise ratio. So you won't really have noise in the stars. So I'm gonna zoom in and show why. I mean, just you get an idea. This image is actually very noisy, and we kind of have noise in the bright areas of the image, but you can tell that it's lower than the darker areas.
Right.
I'm gonna make the mask. How do I make it? For this thing I said before, I want to separate the high signal to noise ratio from the low signal to noise ratio. That will be separating the brightness from the background. So from that reasoning, I will use a luminance layer, and that's I do it by pressing this button in the upper left corner, which says extract CIEL component, right? This is the luminance component of the image. What will I do with this image? Okay, I can't apply this as a mask, right? Because this actually has a lot of information of the background. What I need to do is convert this into a usable mask. And how do I do this? In the way I do this is to crush the dark values, right? I'm gonna completely separate the brightness from the dark, from the background. So what I do is I open a histogram transformation. I take the luminance, and what I'm gonna do is just wait. I'm gonna here crush the dark, so I have a okay. So this image has a very high amount of stars, so that's why you can see kind of a cloud, which is the actual Milky Way area. So that's all stars, but you can see here how we are kind of separating. You can see here in the bottom right corner, bottom left corner, you can see the nebula, and in the other area you can see the stars, and with pitch black background. So this is kind of ideal. You can still do it better than I with just fiddling with the numbers. But this is the how you procedure with this. These are the steps how you do it. Okay, I'm gonna apply this. Maybe a bit less. Here I have my mask, and the way you apply a mask to a image is you grab it by this sided tab we have here, and you click it and you drag it into the image, into the left bar. You just drop it there, minimize this, don't close it because you will have to do it again. And here you have the mask applied. So the red color will show you what is being protected, right? So right now, the stars are not being protected. So what depends on what you want to do, you can invert the mask. So in this case, because I want to touch the background and not the stars, I'm gonna invert the mask so the stars are protected, right? I'm just gonna go mask, invert, and there you have. The stars are protected, the background isn't. So now you can just go into the program and start moving sliders, numbers, and see where it gets you. I'm just gonna do like in exaggerated way so you can see the actual difference, because the best way to do it is to have like very specific like not much I don't know how to say it, but like a good noise reduction is not like going from the image to a lake with white points, right? You should have some data that you can see. So that's what I wanted to transmit, you know, like don't overdo it.
Yeah, don't over process.
Yeah, that's the word.
Yeah.
So I'm gonna grab again a preview. I'm gonna make a preview. So here, well, I mean, you can already see a hot pixel here. Okay, so maybe you can see it, maybe you don't because of the compression, but there's a huge amount of noise here. So what did we learn about the wavelet analysis is that in the very small scale, we should do luminance reduction. And then in the bigger scale, we should do chrominance reduction, right? That's what we learned about the analysis we made. It can obviously differ from image to image because the objects are different, the cameras are different, and the scopes are different. So we are gonna do you might not see the result, you might not see the difference because of the video compression, but I'm gonna try to crank it up in the incorrect way that you shouldn't do it, so you just get an idea of how the program works step by step. So I'm gonna go noise reduction. Let me do a better zoom. I just press this layer 1, click noise reduction. It will load. And I think here I'm gonna go back and forth, Control-Shift-Z. Yeah, the difference is minimal. Like oh, sorry, I didn't change to luminance. My bad. Here. I mean, it's still very, very little. So I'm gonna try the same in a bigger scale. So we might see a change. There.
Yeah.
Did you?
Yes.
Yeah. Okay, so is it? Yeah, I forgot which keyboard combination is to go Control-Z, but it's I think Shift Control. I forgot it, but yeah, you can see how it works. So the brightness of the noise went down, but the color didn't, right? Because you can see some small color squares, right? A small grouping of color squares. And well, I'm gonna just apply this. I mean, this is horrible, right? You should never have an image that looks like this. Just like a little bit less. It's just so you have an idea. Okay, I'm gonna zoom again. It's loading here. Okay, okay, now I'm gonna do I'm gonna reset and I'm gonna change to chrominance here. So I'm gonna work with the bigger layers, the 4 and 8. I'm gonna click the 4, the 4 scale, click noise reduction. Yeah, it's really hard to tell. But the idea of doing the reduction is what you should have in mind. Okay, yeah, here I can notice that there's a better average of colors that went down.
Yeah.
Instead of the super saturated noise that we had earlier. I mean, I can always crank this number up and just click amount of iterations. I can just go 3. Just go crazy with it, and this will eventually go black and white if you keep going. It's loading. Yeah, it will take a sec. But yeah, I'm gonna apply and do a back and forth with the main image, and you will see the difference between. So yeah, another tip for noise reduction with this program in particular, instead of doing an amount of 1 and 1 iteration, what you should do is do an amount of 0.333, so like 1/3, and 3 iterations. You know, like you just flip it. That's that's what I read in the PixInsight forums. It works best because of how the algorithm works. So yeah, I actually found better results, like very specific results, but it actually differs and you get a better and more natural type of noise reduction. I'm gonna close this, I'm gonna reset this, I'm gonna close this. I'm gonna not show the mask anymore. And I'm gonna go from non-noise reduction, this, to this, right?
Big difference.
There's a, yeah. And I went crazy with the numbers. You can get a more natural look, which is the way, because this is just so you can actually see the difference. And yeah, that's it. That's the name of the process. That's multi-scale linear transform. It does noise reduction in a linear scale.
Excellent.
So yeah, that's noise reduction.
Thank you.
Why? Because there's data that it's bothering that shouldn't be there, and you just apply an algorithm designed by people that know about astronomics, right? It's computer science engineer that is talking to his friend, which is an astrophysicist maybe, and they say, okay, so this algorithm does this. Which are the values that we should use, or which type of pixel search we should use? So this is mathematically correct, and the result is this magical program called PixInsight. So yeah, that's noise reduction with this particular process.
Thank you, Augustine. Thank you. A lot to learn, but once you've mastered some of these tools, it's very rewarding.
Yeah, and I still keep. Oh, sorry. Yeah.
No, go ahead, Augustine.
Yeah, no, I was just gonna say that I'm gonna stop sharing. I was gonna say that there's a lot of there's a tab called script in the program, and it's, I don't know, it has 15 scripts. What they do is very useful for image analysis because it lets you understand either image processing or an actual photo for astronomical information, like not only the noise or like the wavelets. No, you can also get the plate solving, which is very useful. You just throw an image there that it kind of has to be perfect, like round stars, because either way it won't recognize it won't do the plate solve. But yeah, there's a lot of scripts that will let you learn about your photo, not only processing, but also astronomic learning, like knowledge. Yeah. So yeah.
Okay. All right. So we have a lot more to move on to, but that was very informative, Augustine. Thank you so much. Up next, we have Rodrigo Zeleda in Chile. And I think he has a live image of Omega Centauri for us.
Hi, Scott. How are you?
Good. Excellent.
Okay. Well, La Serena is clear sky, and I put my telescope to the Omega Centauri, and I share with you my live image. Okay. Do you see my screen?
Oh, yeah.
Oh, nice.
Yes. This is a live image of Omega Centauri with my RC telescope.
Beautiful.
Yeah. I reached a technical problem. My RC is little discollimated, but it's no no bad.
Excellent. It's a beautiful image.
Yes, I take more pictures this night to process it and the final photo. This is a live image.
If you want to understand Omega Centauri, it says here that it was discovered, first identified as a non-stellar object by Edmund Halley in 1677. It's 17,090 light years away. It's the largest known globular cluster in the Milky Way. For the Southern Hemisphere, this is an easy naked eye sight, but in a telescope, it's just utterly spectacular. So thank you for sharing that, Rodrigo.
Yeah.
So Scott, from here in Virginia, I've seen Omega Centauri only a couple of times, and I had to make great effort to do so. I'd go up to the mountains, get a good amount of elevation, and look down to the south, and it would be typically, it would be about June, beginning of June or so, and it would come across the meridian well after dark. And even at its highest point in the sky, it was only about 2 degrees above our horizon. Yet, even with binoculars, you could see the potential that this object would have had it been higher in our sky. It still was easily visible, only 2 degrees above the horizon. It was amazing.
Yeah.
I love that object.
Yeah. Imagine the view that that they get down in the Southern Hemisphere of this object. It's just
absolutely.
incredible.
Yes.
Incredible. That's great. Okay, so Jerry, who do we have up next?
So thanks, Scott, and thanks, Rodrigo, and Cesar and Augustine. That was great. Appreciate your time. So we have actually we have Myron again. He's going to talk to Max, I think, and show what you guys have been up to at the MSRO.
Yes. I've been very fortunate to have the privilege to work with a very talented and just exceptional high school student. His name is Max Dubnowski. He's a senior this year. I believe his high school is in not too far from where MSR is located in an adjacent county, and he has been participating in a capstone project, is what he calls it. It's a requirement to graduate, and they give these students a lot of flexibility in what kind of topic they want to actually research, what kind of project they want to do. And he contacted us at MSRO saying he'd like to do something with astronomy that involved spectroscopy and or measuring brightness of stars, photometry. And so we discussed the different avenues that he might approach. And he decided on studying the light curves and spectral characteristics of RR Lyrae stars. And fortunately, we were able to give him enough time on our telescopes that he made literally probably close to 1,000 observations over the past year and a little more than a year while he's been working diligently on his project. So as he's finishing up his project, which he's getting very close to now, he's asking now, what can I do next? And I think he has been inspired to pursue perhaps an interest in astronomy. And so we are going to be working, I'm sure, and seeing more of him in the future, even after his capstone project is over with. So at this time, I would like to turn it over to Max and let him share with us some of his results. So Max, the floor is yours.
Yeah, thank you. Can you all hear me very well?
Yes.
Okay, cool. So I'll pull up this presentation. And I would just like to say I'm really honored to speak here. It's really, really cool stuff that I've seen.
We're happy to have you, Max. It's great. I haven't been able to talk to you before, but I appreciate the work that you're doing.
Yeah, thank you. All right, so let me just get all my stuff in order. I don't know if there's a way to move this, but we'll just put that there. Okay, so as Myron was saying, I studied RR Lyra, and I ended up doing a project studying the applicability utilizing some low resolution spectroscopy to study this star. Just a little bit of a, I guess, oh, it says it's paused. Oh goodness. Can y'all see my screen?
Yes. Yeah, we still see your screen. It's the first page. You've got the applicability of low resolution spectroscopy.
All right, did that change?
No.
Oh,
now
goodness.
now it's full screen.
No, I went to the new. Yeah, it's changing. You're going to
Okay,
each
it's
slide.
changing now?
Yeah.
Okay. All right. So did that work? Are we on introduction now?
No, still on your first
No,
slide.
yeah,
still.
no, you are. I see it.
Okay.
You too.
Okay.
You see it? It looks like it's on the screen.
Yep.
Yeah.
Okay, I got it now too.
All right. So I just wanted to give a little background to what RR-Lyra variables are, so this project makes a little more sense. So RR-Lyra variables are short period radio pulsating stars, which are older stars typically, and they're located at the intersection of what's called the instability strip. So I don't know if you guys can see my mouse, but it's right up here. And it's at the intersection of the instability strip and the horizontal branch. So generally older stars. And the star I studied was RR-Lyra, which is the brightest of the RR-Lyra stars. It has a period of about 13 hours from minimum to, or from maximum all the way to the next maximum. Its period, or its magnitude typically varies between a little over 7th magnitude all the way down to a little bit over 8th magnitude. And the spectral class varies between an A5 and an A7 or F7 from minimum all the way up to maximum. There is an effect that RR-Lyra does experience called the Blasco effect, and that is a periodic variation or modulation of both the amplitude and the magnitude, or the magnitude and the period of RR-Lyra. And the RR-Lyra has a Blasco period of about almost 41 days. And with that, to study RR-Lyra, I utilized some of the equipment at the MSRO, including the 102 millimeter refracting telescope, the star analyzer, spectral filter, and I was able to come up with some really neat stuff. So I don't know if you guys can see this image. It's a little blocked on my screen right now, but there's a RR-Lyra stack. So this is the actual spectrum of it. And I utilized stacks of 15 exposures, and each exposure was a 40-second with a 20-second delay before the next one. And to determine if the variations were actually due to RR-Lyra, I utilized a comparison star, the Henry Draper 183473, which is a non-variable star. Another method, or another problem I guess I ran into, was actually determining the phase of RR-Lyra. And a little bit how I did that, how I determined the actual phase, is I took the date and time of a maximum from the AAVSO website, and to get the phase of a requested time, whatever time that may be, I took the period and I just continually added successive, I guess, periods onto that before there's a time gap that was less than the period. And when that time gap was less than the period, I ended up just dividing it by the period, and it gave us the phase of the star. And here's just a little Python script to show just exactly what I was doing, but I won't go over that. Through studying the comparison star, or looking at the comparison star, there were 3 out of 7 nights that I actually observed that were clear enough that I thought were good enough to analyze. And what I was looking for was variations in the spectra, because our comparison star should not be, I guess, varying, since it is a non-variable star. So if there were any variations in that spectra, I either threw out those data points, or if it was consistent over the entire night, I threw out that entire night. And as we see, I threw out a few nights. So only 3 out of the 7 nights were really fair for RR-Lyra. Now, even though there were only 3 nights, I captured about 71% of the light curve. And unfortunately, because there are only 3 nights over the entire month, The first night was the first data point, and then the last 2 nights of the observing session over the entire month were the only 3 that were used. So that occurred over about 50% of the Blasco period. At the beginning of the summer, or the beginning of the observing sessions, there was a minimum, Blasco minimum, and at the end there was a Blasco maximum. So that did cause a little bit of trouble in understanding some of the variations and what causes variations. However, even over that 51% of the Blasco period, the calculation of maximum from the code was only about 1.8% off. There was only an error of less than 2%, which correlated to about 15 minutes. And I do want to talk about what I created over here, and I call it the synthetic light curve, because what I did is I calculated through these images, like this one, the field of view of RLR, I calculated a bunch of light curves and extracted the period, or not period, but magnitude, the visual magnitudes of RR layer, and I plotted them along with the phase and created a nice RR layer curve. And there are some particular features I do want to point out on this next slide. And there's actually shock waves going on in the expansion and compression of RR Lyra. So the first one, I call it the first shock wave. And some literature sites will call it the first apparition, or it coincides with the first apparition. It's a typically short, I guess, shock wave that passes by, only occurring over about 4% of that light curve, and it's caused, the shock wave is caused by, or I guess not the shock wave, but the increase in brightness is caused by the shock waves created from the partial ionization zones, which actually cause the star to pulsate, expanding, reaching the edge of the upper atmosphere, and exciting hydrogen and also oftentimes helium to emit light. So what we should expect around this period are some hydrogen emissions and possibly even some helium emissions if it's great enough. Mm-hmm. Now with the second shock wave seen in the synthetic light curve, we can notice it's a little longer than the first one, occurring over about 14% of that light curve, and it's caused by the compression of the star. So the first one was caused by the shock wave reaching the outer atmosphere, and now the second one's caused by the upper atmosphere is actually collapsing and reaching the lower and supporting layers of the star. So again, this brightness or this excitement should cause some hydrogen emission. As we'll see, it actually did not, because it was not energetic enough from what I found. And now moving on to the next slide, I looked at the individual snapshots of all 3 of the hydrogen lines, so hydrogen alpha, beta, and gamma, or I guess the 3 prominent ones in our layer. I just want to, I guess, before we go into what all this is, I guess I should probably explain what these are. These are actually the individual snapshots of the spectral line, and this first little block is, I guess, correlates to this bottom phase right here. So it's the descending branch, I call it. This middle block is the expansionary phase. So they occur over this period right here. And the last one is what I call the post-maximum. It's right after maximum. And I guess maximum in this case would be a phase of either 0 or in this little middle one, it would actually be 1, but it kind of goes to 0. So you can think of it like that. What I did find though, however, is in the descending branch, there was very little activity in the hydrogen alpha lines. And as we can see, this descending branch also coincides with the second apparition. And we can see there was no hydrogen alpha emission over this period, or I guess this phase of the star. Now the second 2, which were quite interesting to me actually, was the expansion phase and the post-maximum, so right after maximum. There were very strong emission features, as one can see in the hydrogen alpha line. I suspect this is possibly due to the Blasco effect, increasing the, I guess, energy of the amplitudes, which causes the hydrogen alpha to emit for longer periods of time. However, more observations are needed, and particularly more successive observations where I can look at individual periods over and over again for a couple of nights will definitely be needed in order to really firmly understand what is causing this emission for such a long period of time. Now, the second spectral line, which I thought was also a very cool one, was the hydrogen beta spectral line. And I wanted to point out that the hydrogen beta was in absorption for the entirety of the spectrum. And I believe this is likely because the hydrogen beta line is near the peak of the spectrum. So the star actually emits light due to its temperature at that temperature range where hydrogen beta absorbs. So I believe that is why we see a hydrogen beta line in the entirety of the light curve. Also, in these next few, I clicked it again. Okay, sorry. In these next few images, or these the expansionary phase and the post-maximum phase, you'll see there's actually a really sharp deepening of the hydrogen beta line. However, afterwards, after minimum or maximum, it actually starts to decrease in intensity again. So that, I guess, would show like a amplitude mechanism behind why the hydrogen beta is diminishing or I guess absorbing in this case. Now, one thing I wanted to point out, which I suspect is the cause for this pre-maximum, I guess, dimming, because on some of the earlier images, you can actually see it being a little brighter or a little more profound in the absorption in this range. So between 74 and 76, the ID numbers, there is actually, that's where the first apparition would be caused by this. So that first shock wave would cause hydrogen to emit. However, because hydrogen beta is always in an emission, I believe, since of the low resolution spectroscopy, the camera or the spectrum was unable to capture both the absorption and the emission. So what happened is it almost averaged out to make a less or a smaller hydrogen beta line. But of course, with everything in this, more data is needed to confirm or deny this. The last line, which I thought was of interest, was the hydrogen gamma line. And there were no emission or absorption features in the descending phase, as you could probably tell. There might be a little something, but nothing significant. However, there were very strong absorption lines right after maximum. And those lines quickly diminished right after maximum, and even in the post-maximum phase where hydrogen beta was still fairly strong and hydrogen alpha was very strong, hydrogen gamma goes away very quickly. I believe hydrogen gamma was lower than hydrogen alpha and the beta line because it's more of an energy level for hydrogen to absorb. So it requires almost a threshold to cause that absorption to happen. And I think that's why it quickly diminished after maximum, because there was not a strong intensity. And just to, I guess, conclude my talk today, the original question at hand was if this was even possible, if I could notice variations, and with a resounding yes, we can see quite a bit of stuff with this low resolution spectroscopy that Myron has helped so much to perform. But another thing I would like to note is the determination of the period using the code worked very well for these timeframes less than the observed Blasco period for RR Lyra. However, with some future studies that are possibly done, like studying the spectral variations over the Blasco period, I would likely need advanced code, or at least take into account the Blasco modulations of the period. However, some other cool studies that I would like to do would include utilizing the MSRO's new 10-inch reflecting telescope, and even studying them in RR Lyra in the earlier summer months to allow for longer observing sessions, because what we did or what I did was wait till the later summer months to actually begin observing RR Lyra. And RR Lyra is more of a early summer star, so it was much lower in the atmosphere, or I guess closer to the horizon, much earlier in the night. So I didn't get as long observing sessions as I probably would have liked.
Yeah.
I think that kind of sums up my project. Did you want to, I guess, talk about the
Yeah, so Max,
Gemini?
that was very, very incredible. It's a very thorough and well put together presentation, and very proud of what you've done with us here. And I hope that your instructors on site will appreciate the hard work that you've done. I know that I certainly am going to be giving you a glowing recommendation in terms of the amount of effort and enthusiasm you put into this project over the past year. So yes, if you would like to, I would like to just share a screen just to show some of the data that we've obtained recently, another light curve basically. So Max is now interested also in doing photometry in other stars. And one of the stars that he's interested in is the U Geminorium. And so what I want to do here is to show you a light curve that he put together, and then a light curve that we were able to make together. Oh, I think we need to, Max, need to unshare your screen first.
Am I still sharing my screen?
No,
Yeah.
you're not. He's not. He is not sharing the screen.
I think the focus is on Max instead of Myron.
Okay, so yeah, I want to share a really neat light curve that he made here not too long ago. What I'm going to do is I'm just going to take us right to, well, it looks like
help.
I think you're still sharing, Max.
I don't think I am, but
oh, maybe it's just a delay. Maybe there's a lag in my.
Yeah, if you're watching the simulcast, there is a delay, several seconds.
Yeah, well, I'll wait for it to catch up here then.
Should be watching the Zoom session, Myron.
I'm watching the Zoom session.
So I don't know why there'd be a delay. You look like you're okay to us when you're talking. So.
Yeah. Go ahead and try to share.
I just did. It still says I can't share my screen. So let me just try something else here.
I can unshare anybody, and I do not see anyone shared.
Because right now my screen is showing future studies with the MSRO, feasibility of temperature determinations of RR Lyrae and other variable stars. So this is still, my screen is stuck on Max's last slide for some reason.
What if I try like exiting out of that? Does that work?
Try that, see if that works. Because I'm still seeing your screen.
Oh yeah, I just clicked out of it.
Oh, Myron just
I guess he's gone.
Yeah, he dropped off. He'll probably come back.
Well, I guess I didn't really mention this, but I did kind of gloss over a few of the points that I made. So if you have any questions about the project that I did, definitely, I guess, email the Mark Slater Remote Observatory, and they will, I'm sure, get in contact with me.
Yes, thanks, Max. That was a great presentation. I guess at this point, Scott, do you want to go ahead and take a break? We've been going on quite a while. We're a little bit past our schedule.
We can do another 10-minute break. We are getting close to the 11 o'clock hour, and people will start logging in for the after party, but we still have we have Lauren Lennon coming on, Molly Wakeling, Richard Grace, Pekka, if he's coming on. So these are some of the people, of course, yourself, Jerry.
Yeah, we're just running a little behind, but that's all right. We'll catch up. We'll catch up.
Okay. So we'll take a 10-minute break now, and we'll be back in 10.
Thanks.
Hello, I'm back.
Hey, Myron.
Yeah.
Hey, Myron, we're just taking our break.
Okay. Yeah, I'm back. My connection got lost or something, so I'm reconnecting now. Hey, Jerry, I'm back on. Yeah, so my everything locked up. It just froze up. I couldn't do anything. So, okay, that sounds good. Yeah, okay, so that sounds good. I am still having a problem sharing my screen. It just says somebody else is sharing at this time. So it's weird. Something's going on. Okay, so yep, that's it. So I guess I'll sign off then. I don't think I'm on anymore tonight. So yeah, I think I will. I've got work in the morning early. So yeah, this was a lot of fun. I appreciated the opportunity. So yeah, yeah. So all right, have a good evening. All right, bye. Okay.
Am I late? Oh.
No, actually, we're not up to you yet, Molly, so you're all right.
Okay, I've seen the floating sign for the after party, so it's like.
Oh yeah, we're on a break. Yeah.
Yeah. Hi, Molly.
Hello.
Hello. Good
Just
night.
All right, let me get one of my telescopes ready to look at something. Get some more light on me. See.
We're almost up to the 1020 presentation.
Okay.
Oh,
All right, I'm going to have a nice hydrogen alpha view of the Cone Nebula zoomed in on the little cone structure here in just a few minutes when the exposure completes.
Well, we're back. Jerry, it's been a great star party so far.
Yeah, I think so. We got a large, pretty diverse range of topics and stuff for sure.
Absolutely, absolutely. What's up next?
So next is going to be, I'm going to introduce Lauren Lennon, our staff astronomer at the Mark Slade Remote Observatory. I've known Lauren for quite a few years. I guess, I don't remember, 6 or 8 years maybe.
Yeah.
When did you join the club? I
for a
can't
long
remember. It was when
time.
you first joined the club, I guess.
Yeah, so probably around 2014. Long time.
Right. Yeah. So Lauren is a professionally trained astronomer, and I wanted her to talk about that a little bit, what she's done with her skills and her career, and what she's interested in at the Mark Slade Remote Observatory.
Thanks, Gary.
Mm-hmm.
I'm probably the strangest professional astronomer that you'll ever meet, and that nowadays I do nothing with it for money. So professional by training, but I actually work in finance now doing investment analysis. When I graduated with my degrees, I was like, okay, I need a job. It was 2012. Job market was a little rough, but I was going around, and one of the things when you get a physics degree, they hand you a math minor for free. But I ended up talking to a guy, and he was like, do you know what Monte Carlo is? Of course I know what Monte Carlo and statistical analysis is. So I ended up here. But before I did investments, I did my advisors, and of course, going to CASE, they were involved with the Sloan Digital Sky Survey. So my research background was on galaxy morphology and classification. And I'll share my screen so you can see a little bit of what I did, but I won't take up too much of all of our time with it. But I studied, oops, is it going?
Yep, we see it.
Yeah, that's good.
The PDF? Okay.
Yep.
So I was interested in these, which are your S0 galaxies. It's a morphological transition phase between your typical spiral galaxy, like you'd think of our Milky Way or Andromeda, and the red and dead elliptical galaxies that you'll see in clusters. And I ended up working on the data set that came through Sloan that actually fed into the Galaxy Zoo. So this is where I kind of diverted from your typical professional astronomer into the wide world of how amateurs are having a huge impact on professionals. So before Sloan, there was never a problem really with, we have too much data. Like, it wasn't a thing. You were like, I need data on, S0s. Okay, here's 10 out of your plates. Go for it. Well, with Sloan, by Sloan 3, which is about when I was on it, there were over 500 million objects in the catalog. Too many galaxies. More galaxies that all the astronomers in the world could sit there and process if they spent all of their days doing nothing but looking at galaxies. So Galaxy Zoo, they crowdsourced it. It's still live, you can go sign up for it. But you'd go through a little training and you learn how to classify a galaxy. So they were breaking them down. So the S0s are in here, but I was going to pull up a sample of what you could see through Galaxy Zoo. So they would put up a picture out of a random one out of the Sloan catalog and ask you, does it have spiral arms? Does it have a distinct bulge? What color is it? Are there weird things going on? Are things interacting? Things like that. So we, within a few years, had thousands of these morphological S0 transition galaxies. So from there, suddenly you'd crowdsource it. So anywhere from amateurs, like people, science teachers were giving this to kids to have them do for extra credit, things like that, to your amateur astronomers who were just interested in, killing some time at work during their lunch break. And they had over 50 million galaxy classifications in their first year. So many galaxies, it was great. So that is what I was doing in my research life a long time ago in a galaxy far, far away.
I used to do Galaxy Zoo back in the day.
It really is fun. After that, I worked at the Shafron Planetarium in Cleveland. So I went more the public outreach and education route instead of staying with the theory and the research. So I taught there for 4 years, worked at the Lake Erie Nature and Science Center and their planetarium as well. And then I became a solar system ambassador. So now when people want speakers for something, of course, everybody wants an astronaut, but there's only so many astronauts. They can't be everywhere at once. So they reach out to the Solar System Ambassador Program. So instead of an astronaut, sometimes you get me. I know it's disappointing, but I bring stickers and things like that. So the kids have a great time at least. But I'll show my pre-COVID setup. So of course, in the age of COVID, not doing this anymore currently because they're closed and that's not safe. But usually I take the portable planetarium out and about and I go to the Udvar-Hazy. I'm a Smithsonian volunteer as well. So as my side.
Oh, cool. I'd like to do that.
For Solar System Ambassadors. They're an incredible program led by Kay Ferrari at the Jet Propulsion Laboratory. And the programs that they give to disseminate the information are amazing. So congratulations. It's not easy. You have to be nominated to be a Solar System Ambassador.
Yep, there are several hundred of us now, coast to coast. We did bring in a new class for 2021, even during the pandemic. So we're always growing, but I take the portable dome and you have to admit that this is pretty much the best office view you could ever hope for.
Yeah, I need to get with you so I can get on with the Smithsonian. I'd love to work on their aircraft restoration. That would be awesome.
Yeah, their hangar is just mind-blowing. But so there's my little bubble, but we used to, shove 60 grown adults into that itty bitty room. So that's not a thing anymore.
That's the Discovery. That's the Discovery space shuttle right next to you.
Yep.
Right. Yep.
Right there. So, like I said, great office view. But that's on hold, of course, until after COVID blows over, and then we'll see what that aspect of outreach looks like in the future. But in the meantime, with MSRO, we've partnered with several of my other solar system ambassadors. We've had virtual watch parties. Amy is particularly interested in it, and our other board member Shannon is also a solar system ambassador.
Right.
So
right.
we all have our fingers in it in different aspects, but that and is mostly what I do is on the outreach side of things for us. And then when projects will come in, sometimes Jerry will shoot me an email and say, does this sound right? And I'll read through their proposal.
Right.
But I'm not very good at the hands-on. Like I think every
well, we've
time
had
I
some
go
training. Yeah, we've had a few training sessions, but they're in between long times in between. So you need to, we need to try to get
practice more.
Yeah. But that's fine. You do great work overall, I think, so with your outreach in the NASA Ambassador Program. So I'm jealous that you get to work in the Smithsonian.
It's fun. But yeah, I'm not so good at the actual lab work as my college professors will happily tell you. Me and mechanical engineering and circuits did not go well together. And I swear anytime I look at the MSRO, it starts to break. I don't get to go in there without Jerry with me for when I look at it wrong, but no, it gives us a whole other level of what we can do and offer since we're 100% remote operations.
Right.
So even during the time of COVID, when our life are these Zoom meetings, it really gives us the opportunity to still continue at least our outreach portion.
I think we're very fortunate to have the people that we have with the MSRO in our local, small town Fredericksburg area. We've got pretty high caliber people contributing.
Oh, sorry, Jerry. I saw a question from John earlier about
Oh yeah, right.
Our spectrograph. We have two telescopes with the star analyzer, the 10-inch RC and the ES 165 millimeter refractor. They have the 200 LPMM spectral grating from Patton Hawksley on them as our spectrograph.
Right. That's called the Star Analyzer 200. And so we only want to put a link to Tom Field with RSpec. He's got spectroscopy software that we use, and he actually donated one of those spectral gratings to the MSRO a few years ago that we have on the 165. And we use RSpec software. So it's the website is Field Tested Systems. And I think it's RSpec. I can't remember.
Spec Astro. I'll put the.
Yeah, right. So you might want to post that. And that software is awesome. It works great. It's easy to learn and use if you're into spectroscopy. And I recommend it highly. And Tom Field's a good friend of ours, Scott. We've spent some time with him at SARS parties in the past.
Yep, he's very enthusiastic, and he makes the science of spectroscopy very engaging and fun, and it makes almost everybody want to try it after he's done giving a talk. So,
right. All right. Well, thanks, Lauren. I appreciate your time and hanging out with us.
Yeah, thanks, Jerry.
I think I'm going to turn it over to you now, Scott, for Dr. Daniel Barth.
Yeah, let's see if Daniel joined us here. I see Gary Palmer. It's nice to see you here. And I do not see Daniel Barth here. So how about if we have Gary join in? Gary, it's nice to see you.
Hi, Scott. Hi, everyone. How are you?
Yeah.
You all good?
Been a busy week so far?
Yeah, every week's a busy week here.
Yes.
It's not slowing down by any means.
Mm-hmm.
So yeah.
Every time I see your room, there's more telescopes, more gear, more cameras.
You have no idea what's coming in this week. It is absolutely mad with stuff. Just
the weather backs you up, right? I mean, the weather is really bad.
That's it. Yeah, I mean, it's like tonight. It is clear tonight, so I'm running tests on the equipment literally all night. So I've just been swapping equipment around because you don't know when it's going to be clear next.
Look at all those toys.
I know, it's really nice because in a sense I don't have to pay for them, so I can sort of take me pick on a couple of places and they say, what do you want?
You can't see me drooling right now.
They just turn around and say, what do you want next? And it's quite nice. Like, what haven't we tried yet? So yeah, but some of it is more involved, you know, it's prototype work or it's other things that we're sort of working on in the background. But yeah, as I said, it's clear at the moment. So at the moment I am on, there we go, M81, M82. It's brightened up just because we're running a sequence test on the software. So when it's in sequence mode, I can't adjust the histogram here. So I've just got it brightened up. And just keeping an eye on focus changes in the temperatures. Really, that's the main thing of this, and also running a test on the sequencer.
That's after 4 o'clock in the morning there, isn't it?
Yeah, it is 4:15 at the moment. So still, yeah, this should finish about 5:20, which is just about when it starts getting light. I did come up with another problem that I need to go out with the black tape tomorrow and cover all of the red lights on the equipment that are shining up into the meteor cam. Yeah, because now we've switched over to another target. The red lights are reflecting off. So that was that side. Prominences, we had a nice prominence today. That was from today. So that was
oh, that's amazing. That's pretty cool.
I shared that on my timeline there.
Thanks. I've got some from the 102, the FCD today. I just haven't had time to process them yet. So we'll be getting those up probably tomorrow.
Okay.
That 102 is a workhorse.
Yeah, it's on everything. It just sort of comes off and then goes on to another side of things, whether it's solar, lunar, or then back onto deep sky. And there's something like about 40 cameras here at the moment. So we're running through different tests. There was a couple of prototypes I was working on today. And yeah, everything's got a different agenda, and it can turn into, when it's clear for 2 or 3 days, it can turn into day and night with the solar and the deep sky. So sort of 2 or 3 hours sleep and then back on with it. But what I thought we'd look at, I did some stuff in the week. I think it was the weekend I posted it up. Adobe has launched a new resolution tool, which is in their bridge. So it will be coming to Lightroom at some point. But what I thought was we would have a look at that, so I can drop that down for the minute. I've already processed this image, and me being, I was having a bit of a clean up at the weekend, so I actually threw away the image that I posted up. So therefore we're reprocessing it again. But basically at the end of the day, it's been processed through on the solar side, and then it's had the wavelets done. And the new resolution tool, if you open that image up in Bridge, yeah, which is sitting there, what this allows us to do is basically increase the size. Now you can do this through drizzle integration and other things in other software, but if you don't have that, then this actually becomes quite a good tool, because it's amplifying all of the pixels by 4, and it's using AI technology. So it's actually looking at the image itself when it enhances it up. So once it's open in the bridge, if you
hey, Gary, I got a question. I know at least 20 years ago, I remember getting into fractal imaging, resolution increasing imaging processing for fractaling.
Yep.
Fractals, do they incorporate fractal technology into this image?
I don't know the full ins and outs of this at the moment. I have found some limitations with it. It seems to be that it prefers working in 8-bit mode on the TIFFs. So if you're running them out of Registax, then you will need to convert them, because Registax saves it as a 16-bit TIFF. So there are limitations there at the moment.
They probably hopped on the convolutional neural network train, would be my guess.
I think at the moment, see, my main thing on this was you always struggle with this with holding the resolution if you want to crop in on solar images, because they're normally coming off of low resolution cameras. So this is the real sort of key thing with this. But you can, your limitation is that Camera Raw will only open up certain images. It doesn't like PNG images. It doesn't like bitmap images. So there's quite a few processes in Photoshop that you actually find, like duotone and things like that, for adding color to these images. They prefer an 8-bit mode to a 16-bit. And you're having this problem if you bring an image out of, say, PixInsight. Yeah, if it's a 32-bit TIFF image that you save it as, then you'll have to HDR it in Photoshop, which is really wasting your time. So you might as well just save it as a 16-bit. But gradually, as you go through the process, you have to change what format it's in. So the easiest thing with this is, once you've got your image selected, there you go, we can open it up in Camera Raw. Give it a couple of seconds to fire that up. And then what we can do is right click on the image at the bottom, and there's a new system on here called Enhance. Yeah, and we can click on that, give it a couple of seconds, and it'll map through the image. Yeah, and then we can enhance the image.
Oh, nice.
Once that's done, you've got the 2 versions there. So you can actually compare these and play around with these and really do what you want. It's totally down to you as to what they are, but you'll see its name's changed there. Once we've got that image, then we can just open it and send it straight into Photoshop. And that means now you can start working on the image. And this is now means that I can crop in here with no data loss. And that's the key, because quite often, once we get in high resolution solar, the whole of this edge here is wasted. It's because of the atmosphere moving around that once you start coming in this close, that most of the image here is going to be blurred around the edges. So what we're wanting to do is be able to crop into this. But if we actually look at the display rate on this now, it's displaying at 50% at that size of image. So it's increased its size by more or less double. And then we can just go into here. Yeah, we can crop the image up. I normally just run a despeckle straight over the image straight away. And then we can move it into a grayscale and then come into the HDR. And that's where you're going to start to notice this now, so that we can start to really play around with the image and draw out some detail in it. And this is one of a kind image. There's no other image like this. So, and then we can go through and sharpen the image up, color it up, and whatever else we want to do with it. But what it's doing is it's giving people the option, certainly if they've got smaller prominences on the sun, all of those sorts of things, where you can actually blow these up without going into other software like PixInsight to do any form of resizing. A little bit noisy that, but do something like that and then just run into a contrast on it. Something like that. So you can play around with this to your heart's content. You know, this is something that you can, but there's lots of other things, smaller galaxies. There's plenty of applications for this in astronomy right across the board. So I thought it was quite an interesting one to play around with.
Wonderful. Gary, thank you.
No problem.
Thank you. Okay, so right now, it looks like Caesar's got an image through his microscope there, which is kind of cool.
Yes, yes, a live image.
Let's take a quick peek on that as we transition over to Molly Wakeling. Okay.
Yeah.
There we are.
Oh, what are we looking at?
He's got an image of looks like a stem plant cell cross section in his microscope. Let me see if I can get.
Yes, it's a pine wood. It's a sample with color of pine wood. The area it's only no more than 3 millimeters, but with a very huge field of the eyepiece is and in the lowest magnification, I can see everything, but it's impossible to explain the sensation when you see through the eyepiece. But something that I can show you is that you don't have limits. Look this. You can see the feel of the eyepiece. never stop.
Huge. Thank you, Cesar. Thank you.
It's a pleasure.
Thank you. All right, Molly, you've got the stage. Thanks for coming on tonight. And by the way, I do want to say that Molly has agreed to also co-host the Global Star Party. So we'll be announcing that fairly soon, in about 2 weeks is when she'll be doing that. So I'm really excited to be to have her on as co-host of this event. Is Molly still with us?
That was me forgetting to unmute myself. I have several speakers lined up already.
Oh, that's great. Awesome.
So yeah, and I've chosen a theme of highlighting women and young people in astronomy. So I'm bringing on lots of women and young people in astronomy to talk about the various astronomy related things they're interested in. And I think it'll be a really fun time.
I think so too.
Okay, so what I have here is a live view of the Cone Nebula, which is it's part of a much larger emission nebula structure up in the constellation Monoceros. But we're looking at this through my 8-inch Schmidt-Cassegrain, which I have a picture of below my face here. And this is using a hydrogen alpha filter. So I'm selecting the particular wavelength with this special filter to be able to see the deep red light here in monochrome emitted from hydrogen gas when it's excited by hot young stars. And there's this incredible structure here in this part of the nebula, this tall kind of cone looking structure that you can see there in the middle. And this thing is several light years long. I mean, we look at it and I can see it in one field of view of the camera. And we're actually at 1,280 millimeters of focal length here. So it's relatively small, this little portion of it. But it's several light years long, and it's this cloud of dark molecular light absorbing dust that lives within this emission nebula and is kind of lit from around on the sides. And it's got there's a star at the top. You can see that it's kind of carving a little hole into it. It makes it look kind of flat in 3D, which is really cool. This is part of a much larger structure that contains also the Christmas tree cluster, which I've seen some cleverly designed Christmas cards with my other astrophotography friends that they send me for Christmas with that star cluster on there. This is currently one of my astrophotography targets. We're looking at a view in Sequence Generator Pro here. I'm currently taking 10-minute subframes. So this is a single 10-minute subframe here. And I'm going to eventually make a bicolor image of this region, hydrogen and oxygen together. And once I get all the data for it. And I have, if you want me to right now, I also have a view of the Orion Nebula in color up and ready.
Yeah, let's see it.
All right, let me switch screens here. Yeah, all right, so let's see, let me change the target name here real quick. And there we go. Okay, so everybody's favorite, the Orion Nebula here. This is a not very well color balanced image, but this is through actually my Optolong L Extreme filter. And let me, this is through my refractor. Let me get that picture activated here. Oh, come on, there we go. This is through my 106 millimeter Takahashi refractor, which I am so very happy to own. It's a fabulous telescope. This is a ZWO 294 color camera that's on here. And this Optolong L Extreme filter is what's called a duo narrowband filter. So it selects those hydrogen and oxygen narrowband wavelengths that I mentioned earlier, but in one filter instead of having to switch in multiple filters to do it. So they're made for using with color cameras where you don't normally want to use a narrowband filter. And my cat is coming to join us here.
The Astro cat.
The space cat. This is Orion. Orion, well, I have the Orion Nebula up, everybody.
Right.
I'm taking 2-minute subframes and live stacking them here to try and bring out some further detail in the outer edges, but I haven't quite got enough subframes, it looks like, to bring out a whole lot. But it's a really cool filter for especially when you live near a big city like I do out here in the San Francisco Bay Area, to be able to do narrowband imaging with a color camera. And it's been a lot of fun to explore that. I just put out my first completed image with this filter of the Rosette Nebula. I'm very pleased with the way it came out. So looking forward to doing more with it.
Awesome.
Yeah, that's what we got for now.
All right. Okay. So let's see who else we have. I think we still have Richard Grace. And I think it's all on you, Astro Beard.
All right, we got a little bit of data that I got from last year. I think they were 2-minute unguided subs that I just messed with a little bit after learning some of the denoise stuff. It's still noisy, but it was way worse before.
Much better now.
Yeah, I'm gonna have to play with that. I'm glad to get some tutorial on that tonight. Always love learning a little piece of Pix Insight. And that's like I said, that was I guess last May, something like that.
I've always loved looking at this galaxy, both visually and in photographs. You know, I've seen I believe 2 different supernova explosions in this galaxy as well, and it's just amazing to think that when you see a supernova in another galaxy, it's amazing to think that the explosion happened so many millions of years ago, and you're just now witnessing it. You know, and it's the fresh energy finally reaching your eyes or reaching your camera. You know, and it's just it's a beautiful thing to witness, you know. And for me, supernova explosions, which there are, you know, I guess several that happen a year in different parts of the universe. It may be more often than that. I remember being surprised at the rate of supernova explosions that actually do happen. But it's every time I see M51, I'm reminding of those nights, you know, observing the brightening of a supernova and then its fade, you know, so it's incredible. And this is just a beautiful object to look at in general.
I hope to see a supernova at some point in one of my photos. A few weeks back, I guess I went back and dug through some images because I heard of one that happened, and I checked, and it wasn't at the exact right time or anything. But it's so interesting to like, oh, that happened when, and you go back and dig through your own footage and start looking for the star, and it was very cool, very cool.
I almost caught one in M66 a couple of years ago. I saw the announcement on the news on like my news feed, and I went and checked my data, and I'd imaged it just like 3 days after it had been discovered. And if only I had looked at my data and go back and compare images.
Right.
I'd also like to point out to no surprise that this was shot with the Comet Hunter. So that is cropped very heavily, and with the old camera, the 183, and I know it was less than 2-minute subs. This was shot from the city, with no light pollution filter.
Very nice. Very nice.
Stop sharing so we can get on with the show.
Well, I think we've actually reached the end of our program. So we had you know, the team from the Mark Slade Remote Observatory on, some really knowledgeable you know, amateur scientists. You know, that's really what they focus on is light curves, exoplanets, you know, and you know, spectra at this observatory. And they're doing it with very modest telescopes, but you know, really applying all the fantastic tools that are available to amateur astronomers to do science. And so if you've ever had the urge or curiosity to actually get involved in a science program, you probably look no further than getting involved with the MSRO, and then maybe joining like the AAVSO or the Association of Lunar and Planetary Observers. And then maybe taking another step by joining as an amateur associate, or I think that's how they phrase it, with the American Astronomical Society. And then they have many pro-am projects that you can get involved in. I'm currently sitting on an advisory board for the American Astronomical Society, and they are looking for more ways to engage amateur astronomers. So there's never been a better time to join. So, I think that's it. Does anybody else have anything else they'd like to share, add, say, do?
I'm going to have Dr. Stella Kafka from the AAVSO on the show in 2 weeks. So you'll hear more about the AAVSO.
Wow. That's going to be very cool. It's going to be very cool. And I see that maybe your cat wants to share something, but I don't know what.
He wants to say Orion's belt is a waste of space.
Terrible
joke. Only 3 stars.
All right. Well, we had a great audience today too. Thank you very much. The next Global Star Party is next Tuesday. So mark your calendars. It will be on at 8 p.m. Central and run till whenever we run out of time. So we're out of things to share. But thanks very much.
Apollo has joined me now too.
Yes, the rendezvous.
Yeah. Yeah.
All right. Well, take care and be safe and have a good night. And as my friend Jack Horkheimer always used to say, keep looking up.
And now, folks, it's time to say goodnight. We sincerely appreciate your patronage and hope we've succeeded in bringing you an enjoyable evening of entertainment. Please drive home carefully and come back again soon. Good night.